Hello, Ashwini ma'am. Are you there?
Yes, sir, yes, I'm there.
Ma'am, we can start.
Okay. Good evening, one and all present here. Welcome to day 4 of our workshop. The AICT sponsored online ATAL FDP on Geo-AI innovations in AI for advanced spatial data processing. On behalf of DY Patil Dean to be University, Ramravadik Institute of Technology, I warmly welcome you all for today's session. So far, it has been an incredible journey filled with thoughtful discussion, insightful exchanges, and meaningful learning experiences. Today, we are honored to have with us Dr. B. Narayan Rao Bogapurapu, who will guide us through another enriching session. Let's make the most of this opportunity to expand our knowledge and continue exploring the transformative potential of Geo AI. Let me introduce Sir. Dr. B. Narayan Rao is currently a visiting postdoctoral fellow at the California Institute of Technology, USA, and a postdoctoral research fellow at the University of Massachusetts, USA. This research interest includes microwave remote sensing for the inversion of biophysical parameters, polarimetric and interferometric techniques, and the applications of radar remote sensing in agriculture and forestry. Sir was the recipient of 2022 IEEE GRSS Mikio Takagi Student Prize at the IGARSS 2022 and the Nike and Rastogi Excellence in PhD Thesis Award from IIT Bombay, India in 2024. He received BE degree in civil engineering from Andhra University, Andhra Pradesh, India 2016, and MTech degree in remote sensing and GIS from National Institute of Technology, Warangal, Telangana, India 2018, and a PhD degree in geoinformatics and natural resources engineering from the Indian Institute of Technology, Bombay, Maharashtra. It is truly a honor to have such a distinguished personality with us today. A very warm welcome to you, sir. Sir is currently delivering a lecture from USA and the current time is 4:30 a.m. So thank you, sir, for accepting our invitation. Thank you so much. Yeah. So today, Sir will be speaking on the topic exploring synthetic aperture radar SAR data on Google Earth Engine. I invite you, Sir, Dr. Bogapurapur, who kindly take over the session. Thank you, sir. Over to you, sir.
Yeah. Hi. Thanks for the introduction and good evening, all. Sorry, I got disconnected somehow. Okay. Hi.
You are audible, sir.
Sorry, it was from my side. For presentation mode, I was just accidentally pressing the F5. Yeah. Can you see my screen?
Yes, sir. Yes, sir.
Okay.
It is visible, sir.
Okay.
Visible.
Thank you. So yeah, good evening. So welcome all for the session. So today I'll be talking on exploring synthetic aperture radar data on Google Earth Engine. So uh, this is the outline of my talk today. So I'll be introducing SAR, what is synthetic aperture radar, and how the data looks like, and how to interpret it, and then also introduction to a cloud-based platform, Google Earth Engine. Then we will go through a tutorial or a demonstration of how we actually write code. Majority of my talk consists of mostly demonstrating along with a basic explanation of how this works and a classic example of image classification using a random forest model using the SAR data on cloud. And if time permits, we can also go through some advanced scripts and the applications and some of the published work using this Google Earth Engine, and SAR data. So coming to the SAR, so SAR is an acronym for Synthetic Aperture Radar, so which is an active remote sensing instrument which sends electromagnetic energy and receives the reflected or scattered energy from the target, and which is majorly, distinct from the optical because of its side-looking nature, and distinct from the typical radars which you find for weather radars or the surveillance radars and other things at airports and weather stations, because it's an imaging radar, because most of the time the other typical classical radars works just time based on a time, so the time and the velocity based on the Doppler. But the synthetic aperture radar is an imaging radar, which means it collects both time delay from the target and also the information of the reflected energy. So here is a typical acquisition geometry of SR. So where we have an antenna which points to a side looking. So I'll explain why side looking, why not another looking like any typical optical sensor. And it is also distinct from the optical. It is an active sensor, so it transmits its own energy and collects it back. So what happens if we assume a typical another looking geometry of SAR? So if we send a pulse which spreads evenly in a spherical wavefront, and if it hits a target which are like on the ground, let's say the target's here at the same distance or in terms of time, so the echoes from these two targets reach at the same time to the sensor, so which makes it impossible to distinguish these two targets whether it is left or right if you consider in case of optical, because in optical we can actually receive the data because based on the reflectance, but here we are actually measuring based on the time delay, which can be which can be solved using the side looking, so where these two targets can be distinguished between based on the time delay of the echoes from these targets. So what we measure, so the SAR works typically in the region of radio and microwave region of electromagnetic spectrum, which varies from roughly a few 1 centimeter to 100 centimeter range. So here, oh, sorry. Okay. Next, sorry. Oh, can you see the screen? Oh, okay, sorry. So here is a list of the bands. So, well, there is no regular order how they name these bands, because this dates back to the evolution of the SAR. So when SAR was invented during the World War time, just to make sure that they kind of mask the frequencies they are using. So military used to use some random alphabet to distinguish their own frequency and just to mask their communication frequencies. So that's how this naming evolved. So the highest remote currently using highest longest wavelength SAR is in P band we call, so which operates in 30 to 100 centimeter range, which is also typically used for biomass and soil moisture studies. There is a coming mission from European Space Agency, which is called Biomass Mission, which operates which is planned to operate in P band, but currently there are no working satellites working on P band. But majority of the satellites currently working in L and C band. There is I think hopefully next year there will be launch of a satellite, which is a collaboration effort from NASA and also the ISRO, which works in both L and S. It's a dual frequency SAR. And today we will be taking a look at the data from LOS2 sensor from Japanese Space Agency, which works at L band, and also Sentinel-1 satellite data, which works at C band, which is from European Space Agency. So often we talk about backscatter in SAR jargon. So the backscatter is typically the reflected energy from a target back to the sensor, because that scattering can be in all the directions, as you can see in the picture here. So when you send out a pulse, depending upon the target nature, so it can be scattered in all the directions, or it can a part of it will be reflected back to the sensor. Typically, there are like three major scenarios. One is just we call surface scattering or odd bounce. So when it hits a smooth surface, let's say like a water body or bare soil, so most of the time we don't get any energy return back. So these targets are visible mostly darker in SAR image. And coming to the double bounce scattering, which is we call like most of the energy, whatever sent from the sensor, it will be coming back to the sensor where we see the highest intensity of the energy, such as like which buildings mostly visible as brighter targets. And there is an intermediate brightness we see on the image from vegetation, which is a mixture of the surface, double bonds, and also the multiple scattering by the vegetation canopy. Further, the intensity depends on uh, different characteristics of the target. Let's say the density of scatterers. So within a resolution cell, what we are targeting. So the density of scatterers also govern the amount of energy we are getting back, and also the size of the targets related to the incident wavelength. Let us say for shorter wavelengths of a C band of roughly 5 centimeters, so majority of the contribution will be from the leaves or the foliage of the canopy. In case of L band, which is 23 centimeters, so it will interact with the comparable size of the targets, let's say branches and the trunk, and so on. And other major characteristics governing the intensity of the backscatter are dielectric constant and the size and the orientation of the target. Let's say the more the more the dielectric constant or the more the permittivity of the target, the more the scattered energy back. And also the orientation. So if it is oriented itself towards the radar, so it will kind of work like a mirror in an optical domain. So it reflects maximum of our energy. And if it is away from the radar, then obviously the energy will go away. It won't come back in a monostatic case because we are having one sensor which is sending and also receiving it from the same position. So coming to how we actually quantify this energy coming back. So there is this classic radar equation we call. So let's assume that we are sending an energy or the power of PT. This is a transmitting power. And also we are not, since we are not sending in all the direction and we have some directionality gain, so we multiply with that. And the wave progresses in a spherical shape. So we account that for like using a 4 pi r square, which r is the distance between the antenna and also between the antenna and the target. Now, a part of this sent energy will reach the target. So this first fraction is the entire amount of energy we sent, and then second fraction is the sigma governs is the radar cross section area, means how much of this fraction actually reach the target, the narrow portion of the spherical surface. And then AE is, then again the reflected energy will has to come back to the sensor in order to us to detect and then form an image. So for that, again, the target itself actually sends out this reflected energy in a spherical form. Again, there will be loss proportional to the r square, and among entire surface area of the sphere, we will get an effective area. We will get a fraction which is equivalent to the effective area of the receiving antenna. So what is a SAR image? So SAR image basically consists of its own coordinate system. Like we will, since SAR works on a time delay basis, so we call it as range or the time domain. So each pixel on this x-axis is a different received at a different time at single position, and a y-axis is called the Doppler or the azimuth direction or the in the coordinate system. So where we will have respect to the movement of the sensor or the each location of the sensor. But in remote sensing domain, we need, which is much more intuitive or coordinate reference to the Earth surface. So we actually convert this actual data, which is called a single look or slant range data, to a ground range data by converting this time and azimuth domain data or range Doppler data, and we assign latitude and longitudinal grid, which is called geocoding, and similar to the optical, but the geocoding in SAR is completely different because we are working with a time and frequency domain here compared to a simple arbitrary domain. And there are two major artifacts or the observation phenomenon with the SAR. One is the speckle, often called speckle noise, but in my opinion, it is much more like a physical phenomenon than a noise. So what happens? Just imagine when you're sending a pulse to the ground, and you have some n number of scatterers in your observation cell. Let's say 20 meter by 20 meter pixel. You have a house, you have a tree, and other so on. So each and individual target which has its own response of the return pulse, and what we get at the sensor is the resultant vector algebraic sum of all those individual sensors, all those individual target response, so which can be sometimes constructively add up to produce maximum magnitude, or sometimes it can cancel out to get a darker patch in the image. So that's why we will see like alternating bright and dark spots, like looking like a salt and pepper pattern on a SAR image, which is called speckle. So which is all, it is a physical phenomenon. There are applications using the speckle and using that as an advantage, or sometimes most of the times in the common practice, we filter out the speckle by using speckle filters either in the spatial domain or polarimetric domain to get smoother images. And the other part of it is geometric distortions. So since SAR is a geometry sensitive, because typical to the optical, since optical now there as we see the distortions of the tall buildings, and we around also the shadows, but in SAR it is much more pronouncing because of its side looking geometry, so that you will have much more shadow regions and also layover is and foreshortening, because since we are actually looking from the side, so whenever there is a flat ground, then we may not have a distortions, but when is there slope or some kind of vertical profile of the target, then because of the circular wave nature, circular nature of the sent wave, and also this topography of the actual ground area which is projected to the time domain, time frequency coordinate system, often either it will be shrink, or it will be overlapped, or it can be completely masked out. So often foreshortening can be normalized using uh, a DEM, a digital elevation model. So since we know how much from how much area the energy is coming, we can normalize with the area, so that you won't see here. You can see a brighter patches where you have mountains facing the radar, which, because if you have, let us say, a 10 kilometers square kilometer image, will area will be compressed into some less like 5 kilometer area, so that you will see a brighter patch rather than actual uniform thing because of the topography, which can be normalized. But the other two phenomena, which are layover, so the actual, if the slope is much more steeper than the radar looking geometry, then your top response will reach the sensor before than the bottom sensor. So these two will be kind of, it is impossible to disentangle these two responses, so in which case you lost the data. And the other side of it is when the slopes are facing far other side of the radar, then obviously you won't get any return from those things. So those are called radar shadows, similar to the optical shadows. So coming to a quick advantages, um, comparing with the optical, so a major limitation for the optical is the cloud cover. Given any point of time, you can find at least 50% of Earth is covered by the cloud, so which makes it difficult for continuous monitoring with optical, which is not the case with the SAR. So we can actually get, since it's also it also carrying its own energy, so you can actually capture 24/7. And also, penetration through the vegetation canopy gives us much more information about the vegetation structure, and also the underlying ground information, which is also a limitation from the optical most of the cases. And which is also SAR is also has a minimal atmospheric effects. Let's say a rain. If you go for a longer frequencies, there will be the effect of the atmospheric parameters, let's say moisture and the rain and other cloud and other parameters will have a lower impact. And it's majorly its sensitivity to the structure makes it much more widely used for physical, biophysical parameter estimation, geophysical parameter estimation from the SAR data. The limitations are, yes, SAR is difficult in terms of interpret for a normal audience, it requires some kind of expertise, like because it is not a direct intuitive image. When you see it, it looks like a grayscale image from like black and white image. But what those pixels means, like how we represent the data. So it requires some understanding of background to interpret the data. And also, as we've discussed, there are speckle effects which makes the image quality much more grainy, and also the effect of topography, where we may also lose the data because of the slope in the topography. So let's take a look at a small animation, how a satellite collects the data. So this is the data acquisition scheme by Sentinel-1. So the Sentinel-1 is a constellation of satellites, one and Sentinel-1A and 1B. So here you can see how it is actually scanning the surface in 3 different subswaths. And also, you can clearly see that it is transparent to the clouds, despite the optical image where we cannot see the ground when there are clouds, but SAR, you can actually penetrate through the clouds. So with this basic understanding of how SAR works and how image looks like, now let's take a look at the platform where we are actually targeting the processing of this SAR data on cloud. It's called Google Earth Engine. So Google Earth Engine actually introduced more than 10 years ago. So which is a cloud-based computing platform, mostly primarily free for all academic and non-commercial use, and where they host these satellite data, not just SAR data, but other type of remote sensing data, optical data, and so on. So they have the archive of this entire more than a couple of thousands of data sets, and they have a interface to access the data and process. They have their own cloud infrastructure without actually downloading that to your local PC. Let's say you can actually use the Google Earth Engine from your mobile as well, like mobile, any uh, electronic gadget which has a web browser, basically. Of course, you can also use that using Python wrappers for a desktop usage. But again, we have to note that the data stays in the cloud and the processing stays in the cloud. And even if we want to export the data, whatever the outputs and the results, again, we have to export that to our Google Drive. Then we can download from there. So this kind of architecture is particularly efficient when you are actually handling their huge data sets. Let's say the Sentinel data set, for instance, the Sentinel-1 collects roughly 600 gigabytes of data per day, and which is difficult to kind of download and process locally. Let's say in yesterday's talk, if you remember, in HPC, they have processed a few terabytes of data, and which took a couple of hours. For that, you need to host the entire data, those terabytes of data, in your PC or HPC or uh, somewhere in the local domain, and then you have to process. But here, since the data is in Google Cloud, you can directly only just save back the output results, which makes it much more flexible for application. And also, coming to the scientific kind of perspective or scientific direction of the Google Earth Engine, there have been a lot of papers recently, like every year, like at least 100 papers, which directly cite the use of Google Earth Engine. Even part of my PhD is also one of paper I published using Google Earth Engine, because it is much more flexible and easy to work with. And during the COVID, when I mean, because I couldn't access the lab and other facilities, so I even did the Google Earth Engine coding in my iPad. So that flexible platform made my work progress in a way. So coming to the interface of this Google Earth Engine code editor. So there are like 3 sections. So one is the data storage, and we have the code editor, and we can store it to the output display and other things. So today we will be taking a look at the web interface, and we will process the basic SAR data of Sentinel and also LOS, and we go through a classification task. Then we will see some examples and applications. So coming to the interface, so we will have, let's say, 4 major windows here. So the left one, where we have all those file explorer kind of stuff, all those scripts, and you can upload your own data, you can upload your shape files or raster data. And at the center, we have the code editor. We do all the coding in mostly JavaScript here. And there is a lot of community support and examples where we can actually directly get those code snippets from. And on the right, we have a typical IDE console and also inspector, and we can see some export and import tasks progress. And on the bottom, which spans an entire screen, is the visualization. So whatever the data we process, if you want to visualize the input or the intermediate products or the output, we can directly import them, and we can also create the geometries or the region of interest and everything on this interactive map. We can again create typical to any GIS platform we have. So we can visualize all the layers, and we can tweak their other properties like the color bars and so on. So if you directly search through the Google Earth Engine data catalog, like with a keyword of SAR, so here are like 7 data sets you will be getting. So where these two are the global, having a global and also the high temporal coverage. Let's say the Sentinel has nearly 10 years of data on the entire globe, which covers the entire globe. And on the Pulsar 2, they've recently pushed like yet 1 or 2 years ago. This is because these two are, first one is the C-band sensor and the other one is the L-band sensor. The second one recently pushed, I think it only covers the Asia region, and it also covers really more than 10 years of data. So without much delay, so let's directly jump into the platform for a basic SAR processing. Before that, let's take a basic steps we will be following today to set up this processing flow. So we read the data or import the data from the cloud to the code editor, what we have seen, we visualize that. Then we apply some pre-processing techniques, let's say the speckle filtering, or we can just clip to our area and do some band math, like converting the units of the SAR data from decibel power to linear, because the SAR data typically stored in decibel format, but that's how we represent the power, just to see much more get a dynamic range. But most of the scientific analysis and algorithmic work would be done in the linear scale, linear power units. So we have to convert that. And then we visualize some data sets, like both in the form of images, and also we can plot some data just to see, and we can export it to our Google Drive for whatever the process data or the output results. So here are the specifications of Sentinel-1 ground range detected data, which is available at in the Google Earth Engine archive. Although Sentinel collects in all 4 polarimetric channels, like, so yeah, the polarimetric channel H, that's the 2 letters indicate the first letter is the transmit polarization, since the electromagnetic wave can be polarized. So we transmit in a horizontally polarized wave and collect the horizontally polarized wave. So which is called HH. So but majority of the Sentinel operates for land in VV and VH. So it transmits a vertically polarized wave and a pulse, and receives both vertically polarized wave and also horizontally polarized wave. So let's take a look at the platform. So yeah, when you actually Google what is Google Earth Engine, and you will be landing at this page where there will be all the tutorial and information of the Google Earth Engine. And you can also go through and the data catalog, where we have ton of data available. And also you can also produce your own data. Let's say you have done some analysis with your SAR data and made some product. You can also push it to the publish it to the users, other scientific community, so that they can also directly pull and use your results or the applications. Uh, so here is the code editor. Where we have seen on the left side, we have all the scripts and file manager. We can access the documentation of this. And also we can upload our own shape files or our own data sets. some data for let's say if, for the data sets from ISRO satellites, ISRO SAR satellite. There are a couple of ISRO SAR satellites as well, but currently they're not available in Google Earth Engine. But still, you can download from the ISRO Earth ISRO's data ISRO's web page like Bhunidhi and other portals, and you can upload it to your Google Drive, and you can access directly, and you can just use this free computing platform. So let's take a look at the Sentinel data. Let's say if you want to import a Sentinel SAR data, you can just type that, and for every data set, there is a code snippet provided here in the document and the dataset documentation, where you can actually copy this and paste it to your code editor, and just to see and visualize the data, how it looks like. So if you run this script, now you can actually see it's a false color composite of an RGB made with pre-seasonal backscatter images. Of course, it's at once it is a complex script, but let's just break down the script into smaller chunks. Let's say, so how you import data. So all the data sets in Google Earth Engine are actually stored in a what they call image collection structure. So all these raster data, what are we call images, are stored in image collection with a unique URL, or the URL referring to the database. So to import that to your code editor, you will just write this line like is engine.image collection. Then on this image collection, you can actually apply a lot of filters, like how much from which time to which time, like the temporal filter, and what acquisition mode of the sensor you need, and what orbit, like ascending or descending, and what polarization channel, like which band you want. Like if you don't want to load all the bands, you can actually select one specific band, and this one, okay. And the third line here, so the sixth line here actually sort the entire image collection according to the ascending temporal order. And you can also sort the images based on, let's say, if you want only images over Mumbai, so you just draw a polygon and just import the images just over Mumbai. So let's see this in action. So if you want to import the image, so as you have seen in the code, so you can directly import as an image collection, and you can actually draw a polygon. Let's say, okay, don't need these layers. You can just toggle these layers off. So these are the geometry tools where you can zoom and also create your own geometries. Let's create a polygon over Mumbai. Take a hand tool. Is my screen visible, and can someone confirm it?
Yeah, visible, sir.
Oh,
Yes,
sure.
sir. Yes, sir.
Thanks. So you can draw a polygon. I mean, as of now, I just draw a rectangle, but you can choose your own area. You can actually rename it to your ROI. And if you just run it, you can directly, of course, you can see nothing because it's just imported to your code editor. You can save your script to your uh, here. All the saved scripts are visible here. So I've just saved it to with an example 0. So in order to view this, like how many, let us say how many scenes are there and how they look like. So we can actually use simple print statement as any other programming language just to see this collection. So how many images, just, and also the metadata of the. So if you use any print statement, so you will be getting this the output on this console. So where you can actually explore and expand this feature. So there are currently 2 images which are acquired in between like June 2021 and July 2021 over Mumbai region. So where you can actually also explore like what are the bands and how they look like. And if you want to quickly add that to you, I mean, just to visualize, add that to your map window here. I mean, if anyone has this Google Earth Engine account, or you can directly create, or you can follow the code also directly, like parallelly, real time. Or I'll be sharing all these codes with the examples after the talk, so you can explore yourself. But for that, you need a Google Earth Engine account, which is free, but it may take 1 or 2 days for activation. You have to fill a form like why are you using it, what is your scientific interest, and a couple of random, I mean, those actual uh, user data form. So in order to add this to your map layer, I mean, to the map, so the image, you can actually use this add map command. So, so map.add layer actually adds 1 image at a time, because as of now, we have a collection. So we have to select any 1 image and a 1 particular band or a combination of bands for the visualization. So here I'm actually selecting this collection and 1 band from the entire collection. So all the images we were selecting the VV and also the first image. And here the min and max are like typical min max for image visualization parameters. And you can pick up a name for that. And if you run this, then you can actually see the entire image. You can actually toggle on and off the visibility of this ROIs or the polygons which you are importing or you just drawn, just to see how the visualize how the data looks like. So what this data means here, let's say the darker patch here, the ocean looks darker as we have discussed. So we only get, I mean, we never get any reflection back from a smooth surface unless there are some waves and some wind blowing on the ocean surface, so that it will make some waves. So some part of scattered energy reaches the sensor. Otherwise, most of the time in calm ocean stays black. But here you can actually see a small dots like structures, which are actually ships, which are bright in this, always bright most of the times, because it is, as we have seen, there is a kind of a double bonds where we get a maximum of energy return back to the sensor, which is like a 90 degrees. Twice it hits the water surface, then it hits perpendicularly to the ship, and it comes back. So minimal loss of the energy. And also it happens same thing happens, the double bound scattering with all these buildings which are kind of oriented towards the radar sensor at 90 degrees. And here you can also see the airport runways, which are flat, which always looks dark in radar images. And currently this image is in power domain, I mean decibel power domain, which is expressed in decibels. So the range of this data, we've kept it like negative 15 dB to a 0 dB. Most of most of the SAR data, if you represent in decibel domain, consist in ranges in between like negative 40 dB to 0 dB. It's very rarely crosses the other side of the dB, or like in the positive side of the decibel. So, but the decibel scale is often mostly used for widely just visualization, not for the scientific analysis. So there are very limited algorithms which directly use the decibel in their algorithms. And also if you see this, there is like lot of, as we have discussed, a lot of speckle also there. If you want to use it without speckle, then we have to apply a filter for each band and each image through the entire collection we can apply. So once we import the data, so now, okay. As of now, we have imported the data and we've specified the required time ranges and also specified the bands and orbital paths. We can actually play around with this, all the parameters, like you can pick up the any other your interested area and check what are the data sets available. Let's say if I just increase this like 21 to 24, let's say 3 years of data. So we have 94 images here, if you can see this. So which is quite fast and efficient to access the entire archive of the data, which is difficult if you process it in a local machine, because for a small scale task, you can actually download these images. Each image would be roughly 1 GB in GRD format. So in order to download this entire archive of like, let's say 10 years of data for one particular scene, so which will roughly consist of a 300 to 350 scenes, equivalent to 350 GB of data. But you can actually process that within a couple of seconds here, I mean, a fraction of a minute. You can also change, like only you can select a few bands, or you can actually change, you can actually check whether there are any uh, images in the ascending pass. Yeah, I mean, interestingly, there is one scene, because what makes ascending and descending different is, since the SAR is geometry dependent, or the orientation, because the ascending pass looks different structure geometry, or the orientation of the target, and the descending pass, it will have a different geometry. So from the same target, from the same building, we can have a different amount of energy return in both ascending and descending. And moreover, these passes are kind of structured in a way that one would be happening in like early morning and one will be in the evening, where you have a different physical phenomenon happening on the ground, which also influences the SAR backscatter. So most of these studies, in particular to the agriculture monitoring or the crop monitoring studies, people use the pass which coincides in early morning to avoid these uh, the diurnal changes or those heat change and the moisture changes throughout the day. Because if you're observing the crop in the evening, which will be in a different state compared to in the early morning. So these all factors you can actually control and get a filtered image collection. From that, you can also go for a masking, because often you will have those edges in the radar data, and also you will have low noise, low power pixels, or the less noisy pixels, for which, similar to any programming language, you can actually define a function, which is here I'm actually defining the edge as less than all the pixels, less than 30 dB. I'm just masking them out. You can do that with your own thresholds in linear scale as well. Then you can directly apply that mask on the entire collection. So in order to connect the function and a collection, we use a keyword called map. So it's kind of mapping the entire image collection with some function, so that it will just apply to through all the images in the function in the image collection. Next, we can also do a band math. So now we have in a decibel scale, so which is a 10 multiplied by log 10 of the actual power unit. So whatever the power received by the antenna is actually converted into decibel scale using 10 log 10 factor and stored in Google Archive. So now if you want to convert that back to a linear scale for the other scientific processing, now we can actually use another function. We can create a function where we are actually selecting each band, and we are doing this band math. So each band we are selecting from image.select. So in each collection, we are selecting one band and we are converting that to linear scale using this formula, like 10 power actual the decibel unit divided by 10. Then we are repacking them into different, we are renaming those bands and again exporting it to a different image collection. So after doing this linear conversion, we can also use the filtering. It is similar to any image filtering. You can also use other more sophisticated polarimetric filters, but also that is limited because we just have two channels. We don't have actually phase, which is also because the SAR collects both in real and imaginary part of the reflected signal. So both the intensity and also the phase of the reflected wave. But here in GRD, we only have the amplitude or the intensity, return back power, but we don't have the phase. So basically this image, this filter will do a simple averaging window with a radius of 2.5, which means it's a 5 cross 5. It will create a 5 cross 5 mean filter. A filter, and it will just filter the entire data to reduce the speckle. So after doing this pre-processing, let's say masking and also filtering and also some band math converting into linear, we can again import that back to your map just to visualize before even exporting. Then we can export it to the drive. So we will do this each step again here in the code editor. Let's say as of now, we have this import the data and visualized it. Now, in order to convert that or mask that data, we will write that mask function, or we can copy paste from that slides. So here is the masking function where I'm using a threshold of 30 dB, and also wherever there is the data less than 30 dB, it will just mask the entire all the pixels in the entire image collection. So you can actually run, which would be very quick. Okay, we have only one image. That's fine because we have selected ascending band. Then we can convert into linear. So I can show you. Mask. Okay. You can now you can actually see there are a lot of layers added. So first one is the dB decibel power. You can actually toggle off all. So this is the original image, which is there. We have imported. So this is the linear converted image. So we have converted that into a linear scale and masked. Now this is a filtered image after applying a 5 by 5 filter. So you can actually change this kernel size to, let's say, a 3 by 3 filter, which will be much more less smoothened. You can see that. Or you can actually notice how quick the process is happening, like within few seconds. Then you can actually export this. You can also clip the data. Let's say I have also clipped with the ROI which I created. Here initially we created just to search the data, right? So this rectangle. So if you don't want the entire image, because the entire image is roughly a 250 kilometer swath, so 250 kilometer wide by some 70 to 80 kilometer in the other direction. So you can clip the data using just dot clip, and you just provide the extent, or you can simply draw on the map and give the name to that. So which will look something like this. So the clip data, if you visualize, so this is your clip data, and you can export that to your Google Drive using this command, export image to Google Drive. And you can select the band name. And if you run this export command, so there will be a task here. I mean, and there will be a task in the tasks window. So it won't be automatically exporting every time you run. So it will create a task so that if you want to export, then you can click the run here so that it will directly create a folder if you have given a folder name and also image description and everything. So if you just run this, so after the processing, you can specify your projection, your pixel size, and drive folder and format of your raster. Or you can also give any other Google Cloud bucket or any other external cloud source if you want to dump there other than Google Drive. And you can give a name to that. And if you click run, so here you can currently see that there are no files in the Earth Engine folder, but it will take some time to actually process and export it to your drive. Meanwhile, we can actually check. So let's say a simple image visualization task like a histogram. So let's say if we want to see like how the values are there, how the distribution of this. So we can actually create those kind of plots to visualize them. So this is a long line of code. So Google Earth Engine has this UI chart.image. So there we have different types of charts. Here in this specific case, I'm using histogram. Then you will actually select the band you want to do, and you just mention all other extra parameters like the x-axis limits, y-axis limits, and how many number of bins you want, and so on. And again, if you run that, the histogram will be displayed after computation. So here in the console window. So now you can see the backscatter looks bimodal, so which is typical for this scene, as most of these lower values are mostly on ocean, and here the ocean, and on the other side your the greater than 10 dB the values, there is another peak here, which is mostly over land. You can also clearly see in the map window. So on the left side of the image, which is ocean, which is mostly darker side. On the right, we have land, which is distinct. And also those brighter spots, mostly those are urban areas, and also some geometric distortions, because we have a mountain range here where we can see those layovers and shadow effect in filtered image. Just wait. Yeah, in the filter image much more clearly than actual image. And yeah, it's in filtered image. So these bright patches, and also you can see the terrain topography. Those are the mostly either foreshadowed or layovered one. So if the slope is greater than the incidence angle or the look angle of the radar, then the data is not useful because it's just alias. They call data aliasing or data overlapping. So those data is mostly not usable. So that is one of the major limitation of the SAR. This topography effect is difficult to handle in SAR. So we can also check. Okay, let's see what happened to our task of exporting that. Yeah, it created less than in a minute. So you can actually see that by clicking here. So then in the task manager, so you can also see some of my failed tasks before. So if this a task is failed, you can actually see why it is failed. Apparently, I've exported a very large image, which with more than like more than a billion pixels, I guess. So yeah, that's why I kept like low resolution. You can actually export. There is a size cap, let's say a 2 gigabyte size on this GeoTIFF size, which is so even if you export a huge image, it will export in chunks. You can also specify this maximum pixels and other parameters while exporting it. Now you can actually use, you can see it's just created 3 minutes ago, which is 1.4 MB, and you can just download it for further visualization, and if you want to process it locally and for other things. So this is a basic kind of workflow you can do. Okay. A basic SAR processing workflow you can do with Google Earth Engine. So you can do a similar thing with the other satellite data, which is available at here. So LS2, but here to get sigma naught is a bit different because the data is formatted in a DN rather than a decibel scale. So you have to use this conversion band math. Similarly, what we have done using the linear scale, then we can convert that. But this is a L band data. You can do the exact same filtering and also the speckle filtering, the temporal filters, and also clipping and other things using the exact same thing. So now we can go for a simple excuse me, image classification thing, how we actually perform. So now we have a pre-processing workflow running. So a typical image classification workflow here consists of a same chunks as before. You read the data, you pre-process. Now instead of visualizing, you also have a classification task for which we are doing a semi-supervised classification using random forest classifier. So we create our own ROIs, the region of interest. We pick up some samples, we train a random forest model, we generate a classification output and classification report. Then we can export that classified image to a Google Drive, to our Google Drive. Here it is much more simpler because you can actually handle huge data sets and entire temporal and spatial domain compared to a local machine. You can exactly use the same architecture in a cloud in a HPC as yesterday as covered in the yesterday's talk. So now let's take a look at a random forest classifier. So until this for this, since we have used Sentinel-1 data, so for the random forest classifier, I'll be using LS2 data. So we can also take a look at the L-band data, how it looks for the same Mumbai region. For that, you can actually create a new file. So rs class, save it. Okay, so here it is. By default, it is copying my previous script to rs class. For which, again, we follow the same thing. First, we need to import the data set. So you can import using directly, you can go to this data catalog just to import. You can just check, search for the LOS2 data set. So here it is, cancer level 2.2, and you can actually copy this collection. All we need is the URL of the data set and our custom date range and other things like here. And also the geometry. So we need a point from which location of the globe you want to have it. So you can just see how many scenes are available here. From 2014, you have 4 scenes. Let's quickly visualize that data. This is L-band. You can see it's okay. What happened? Oh, the ROI is not specified. Sorry. So you have to draw an ROI in order to visualize that. So here is my ROI. Okay. Now run it. Yeah. Okay. Instead of a grayscale here, if you see, I've created an RGB using all those 3 bands we have. Yeah, let's see. So the red channel is HH and green is HV and LIN is the local incidence angle. Again, note that as of now, we haven't done any conversion. We just got the collection. We just selected the first image. We clipped it with our custom ROI and we created an RGB selecting 3 bands. And then we just added it to the map using some scaling of the data. But still the data is in DN. So you can either you can convert into decibel or you can actually directly use it for classification as well. But for that, you need to have your training data. So to train, let's say we can actually take a couple of pixels here. I have already created some training data and also validation data because just to save some time for us. Where you can directly add that here, all the ROIs. So I've created some forest pixels and water, urban, and also some bare soil. Okay, if you actually, you can also create by using a linear string of vertices, what you call lat long vertices, or you can directly draw on the canvas as I did before for the ROI, which I can see here. Now we can also convert these manually typed coordinates into those ROIs. If you click convert, so you can see that all the uh, training data and validation data I've created, you can clearly see here. So yeah, I've taken here. You can actually modify by clicking on them. As of now, I'm just masking this out. So yes, these are the training and validation data I created for forest and water and so on. Okay, now if you click enter, okay, nothing happens apart from this image, the display of this, because we haven't wrote any code to prepare the training data. So So since we have the polygons drawn to sample the data, so we can actually sample the data from the rasters to train the random forest classifier. For that, we have to create features. So we can, so each polygon, I'm assigning a name of class and attribute. So I'm assigning a number. So let's say forest, I'm assigning a number 0, and for water, number 1, and so on. And then I'm grouping them into training polygons, all the classes, the forest, water, and urban and soil, bare soil class. Then I'm sampling the data using this sample regions. So I'm using all the polygons and some scales. So this scale makes sure that it just aggregates the pixels and pick up the mean value from that. And because by default, the scale, the actual resolution or the pixel size is 10 meter, but I'm just sampling at a much more coarser resolution. So now you can actually visualize the training data just to see, is there any data set sampled? Because sometimes it can happen that if there are no scenes or otherwise, so if there are issues, then you don't have any, you will not see any features in the training data. So yeah, now you can actually see there are like a lot of features. So it can only print maximum of 5,000 elements. So for which you can actually select a few elements and print. Let me select. Let's see, let's visualize this later. Since we have the training data ready, so we can actually train the classifier. We can just define the classifier with some number of trees, because it's a random, it's a decision tree classifier of random forest. Now what we are doing, so we are defining the classifier. So this is the function to call random forest with a parameter. Here we define the number of trees in the classifier. Then we provide the training data, which we created on the top, and the class is this, what we defined for each class, so which is identified by a numeral. So this is a label, and we can select the input bands. We can select all the bands. In this case, it's just we are training on one scene. We can also do it with the temporal. I'll show you that. So entire stack of all the available scenes and all the bands, you can do that. So just to classify, so now we created a classifier. It's just one line command. So just use the selected bands which you created before and use the classifier just to classify it. So if you're right, okay, nothing happened, but classification is done. So just to visualize the output, you can actually add this classified layer to the map. So this is your classified layer. Since we have 3 classes, so 0, 1, 2, 3, and I'm assigning one color to each class. So now you can actually, if you run this, now you can see classification output. Okay, now you can toggle this off to clear off some space. Okay, so now you can see with simple basic 4 class image. Of course, there are like, if you see this ocean, which is also, this Thane Creek, misclassified as a soil because of the waves and the turbulence in the thing, and also we are using just 3 bands and one scene. You can also improve that by selecting better training samples and temporal data sets. And so after this, let's say a classic approach the classic approach in any classification algorithm is to generate a classification report. So in order to do that, we have to also have a validation data set to validate and just sample and generate. So similar to this classification, whatever we did before the training ROIs, we can also create a validation ROIs. So in the same class, so this is my training ROI, and this is, okay, sorry. Yeah, so now you just, I can delete this. I just want to delete, just coming in the way. So this is my training ROI, and I have created a validation ROI. So this is my training. You can see what our training class this is, and this is a validation ROI. So I have both. So again, we have to create again the same sampling scheme. So we have to sample all these with the validation data set, same as sample regions, and define exact the same features we import. Then to create a confusion matrix on the top of this reference or the validation data set. So you can directly create, so the different reference data is our sample data set and just dot error matrix. And we have this class, and input image has this classification band. So now if you run that, then you can see a confusion matrix in terms of a list with the 4 classes and number of pixels classified. You can see there is a couple of misclassification between 2 and 3, which are which is for a forest and urban and soil, I think. Yeah, the third set, class 2 is urban and class 3 is for soil. And also we can calculate the kappa coefficient, the Cohen kappa coefficient, and also overall accuracy. For that, you can just write the confusion matrix dot accuracy, you'll get the accuracy, and confusion matrix dot kappa, you'll get the classic, the most widely used these accuracy parameters. Of course, you can see these are all 9, 9 because I just selected very limited samples and the 4 classes. So you can actually we can improve this with a more number of classes and also more number of bands, means in the temporal direction. So if you do the same classification, let's say with all the temporal bands. So here we have taken one image out of these 4 images and 3 bands, and we got this image. So we have this misclassification, just you can remember. So while using a temporal one, you can have a better classification map than this. So to create that, you can create a new file. So RF temporal. Okay, so you can create this. Okay, I can actually show here. I have already written script for the temporal one. So if you run this script, oh, this is temporal RF script. Yeah, where you can actually see the classification output, which is much better than previous output with a more number of bands. So here I've considered 21 images. So I've just compiled them into 63 bands. So 21 multiplied by each has 3 bands, and then I run the same classification algorithm. So you can improve this. Of course, you can also combine the Sentinel-1 and Sentinel LOS2 data to build upon these things. So further, since we have looked into the simple basic classification one, now we can also take a look at more advanced scripts and also a few applications. So where this can be more useful, and also some challenging tasks we have also done before, which we done before. So one of the tasks we have attempted is monitoring the wildfires using a dual polarimetric radar vegetation index, which is a combination of VV and VH. So where you can see these are the outputs generated from Google Earth Engine. On the left is before wildfire event, and on the right we have after wildfire event. So we have done a temporal analysis, extracted these values from the Google Earth Engine, And here we can clearly see the radar vegetation index, the drop in radar vegetation index. Since we have data, I mean, we have the data from both ascending and descending passes, we can actually we can process them separately and plot them, and we can clearly see the drop of vegetation index during the incident. And after that, if you see in the ascending pass, there is again a vegetation regrowth for about an year, and then it almost reached the previous state. So you can say, okay, so now this can be done using a local machine as well. If you have a huge computer, let's say HPC like yesterday. So I processed nearly 5 years of data here. So 5 years multiplied by 30 per year, the 150 scenes you can get. So each data here with a mean and standard deviation of the radar vegetation index. But how far we can actually push this Google Earth engine? So for that, we have attempted a global scale forest type monitoring using the same vegetation index, the dual pole radar vegetation index. So here is the major forest types at a global scale. So there are like 5 major forest types, and we have divided them into several regions based on the latitude. Then we plotted, so for the north temperate region, so northern temperate region, which is the zone 2 here. So we have 4 major forest types, the needleleaf, evergreen, and deciduous, and also deciduous needleleaf and deciduous broadleaf. As you can see, there we have processed nearly 7 years of data for the entire globe. So just now you can actually imagine the scale of this data processing here. I mean, using the Google Earth engine. So let's say each scene is 1 GB, and we have entire globe for 7 years. So 7 years, so which is not even terabytes. It's even the processed output data is like an order of 4 terabytes, which I'm sure, I mean, it's kind of nearly challenging and nearly an impossible task to do with any HPC directly by downloading, because you have to download the entire archive of Sentinel data, which is few petabytes. So these kind of huge tasks you can actually do with ease using this kind of cloud-based infrastructure. Here, what you're actually seeing is the seasonal variation of the vegetation in different forest types. So where you can see there is a clear seasonal trend in the forests at C-band. If you take a look at the tropics where the C-band saturates, let's say, I mean, C-band saturates such a dense vegetation canopy where you cannot see through the canopy if the canopy is too dense, where you have to go for the higher, longer wavelengths like L-band or P-band. So here it also shows, the analysis also shows the limitation of the C-band, where we can use the C-band and where are the limitations, and when we have to go for L-band. Let's say the future NISAR, which will be launched in few months, is planned to launch in few months, expected to provide us a similar consistent data in L band, which is openly available, and we can take a much more deeper look into the tropics or the rainforest and tropical forests. And other advanced scripts involves, there are a lot of cloud resources available, which part of my thesis is one of these dual pole descriptors. Which I've done is, basically this script generates, if you give your sampling points or some input as your sampling points in the temporal period, it will extract all those GeoTIFF files and export it to your Google Drive, and also saves those temporally sampled data into your CSV file. For each data point, you will have entire temporal series of backscatter, and also these pseudo entropy, scattering entropy, and other parameters as mentioned here. So, but all this, as of now, we have discussed about the actual real-time processing of the data, which requires an account. There are other mode of Google accessing the Google Earth Engine, which is Google Earth Engine apps, which doesn't require any login, because these are like kind of output of your scientific research or your study. Let's say if you have some maps created and if you want to share it with others, anyone can access and download and access your data, which as part of this, I've created an app to visualize these parameters, which can also be, I can actually copy this URL. You can even visualize and download these parameters from literally anywhere on the globe for any temporal period, from even in your mobile. Let me see. Okay. I'm just sharing this link. You can directly access it just to see. Okay, can anyone confirm is the link working, or you can just play around with that, and you can also download those processed dual polarimetric descriptors. If you are like don't want to directly jump into the coding, you can directly use those GUI interface. I can actually give a quick demo of it here. So this is how the app looks like. So you can select. So these are currently centered at agricultural fields over Canada, where I mean, because these are ideal conditions for agricultural monitoring, because these fields are like 1 kilometer by 1 kilometer, and much more. We have a lot of crop data and other things so that we can directly cross compare. But you can actually do that for any part of the globe. Let's say if you center somewhere, if you want to do it for the Mumbai, so you can just zoom out to the Mumbai region, and all you have, once you are like centered the scene, all you have to do is just apply filters. So it will just process whatever the first available scene over that region, and it will just display. Like you can actually select all those parameters. So currently it is displaying the scattering entropy. So on vegetation, you can see a more scattering entropy compared to a much more bare soil, and flat grounds and water bodies are mostly masked out here. You can also actually see the vegetation index, the dual polarimetric radar vegetation index, where you can see the bare soils like darker blue versus the little bit of yellow. And also you can change the temporal range, and you can select your any specific scene. Even if you select like a huge temporal range, let's say 5 years, but you can only visualize up to 10 images here. That is the limitation. And also you can, let's say if you like some, if you want to download this data, so all these bands, so you can just zoom into any region like this, and you can click on the download button. So there will be a download. So you can directly click on the download. So it will download you all the layers, clip it to the map extent, whatever you are visualizing here in the app. So these apps are like advanced things to distribute your research output, and also for kind of non-domain users if you want to do. So it requires no coding knowledge, just you can interact with your app, and entire real time the data is processing. Let's say even if there is a collection, maybe tomorrow, like yesterday's collection or before the previous week, you can the app will take care of, because as long as the archive is updated, you can actually get the near real time data updated and get your processed data here. So anyone can please confirm, are you able to access this app? And just, can I get a thumbs up?
Yes, sir. This link is working.
Okay, sure. Thanks. So for further exploration, you can actually go through these resources. There are a lot of resources, YouTube tutorials and other things, how to use the Earth engine. And in specific to SAR, yes, we need some expertise of the SAR to play around or with the SAR data. And with that, I think I finished in time. So I think we can take some couple of questions. Thank you. Thank you very much.
Yes, sir. Thank you, sir. Thank you, sir, for sharing your valuable insight with us. Now it's time to engage with the QA session. Participants, please feel free to ask questions.
Excuse, sorry to interrupt here.
Yeah.
Yep.
Hello.
Hey, yes.
Yeah, this is I'm Brahmaramba, and I have a question. Like, sir, I'm a beginner. Actually, I'm a PhD aspirant. Sorry, PhD scholar, and I'm a beginner here. I just wanted to know, can you please share the code for our practice? Is it
Yes, yes,
possible?
yes. All these codes will be available. I'll share all these codes, whatever part of tutorial with you after that
Okay.
talk. Yeah, and also you can actually have these advanced whatever these app and the advanced scripts are also
Yep.
available on my GitHub, so you can actually access them. They're
Okay.
already there. So yes,
Fine, sir. All right. All
even
right.
the
It was a
code for
nice
this
session.
app
Thank
also you
you.
can just, yeah, sure, sure.
Yep. Yep.
Welcome. Yeah.
Thank you.
Yes, any other participants wants to ask any question?
Sir, hello.
Yes, yes, please.
Sir, can we export real-time data here?
Uh, can you be kind of more
Sorry,
specific, like
import.
what kind of real-time data you mean? Right. So we can export as long as the data is available in the updated in the Google Cloud. I mean, from the cloud to your Google Drive or your Google Cloud account.
Okay.
So let's say
And
I think there is a latency between of like let me quickly check. Let's say it's today's date, so 24. We can actually check that directly. 12/5. Let's see how many data sets are available currently. You can actually check that. It will be updated. Is there any data set available in between these, let's say, in this month? And if you apply filters, okay. Apparently, there is no data available for this particular region in 5 days, but we can actually go a little longer because the temporal revisit of this Sentinel is 12 days. So let's say
okay.
there is data set which is covered in November 27, so which is 10 days ago, not less than 10 days ago. So
Is
yeah.
this data readily available in Google Earth Engine, or we need to import from other platform?
No, these are directly available in Google Earth Engine. So these data sets, all the data sets are like they're pre-processed and stacked and in like all this same grid and everything. They actually kept it in Google Earth Engine. It's a separate repository.
If we download or import some data from other platform, and we can import here
Yes.
also, is it possible?
Yes. So here, if you can just see the screen, so there is this assets tab. So here you can actually upload your own data sets, either shapefiles, CSVs, GeoTIFFs, everything.
Okay.
So then you can directly import
Just
that.
for an example, you have shown classification example.
Yes.
Similarly, for object detection, if suppose is there, so from
Mhm.
SAR data, is there ground truth available?
For object detection, what kind of objects you're targeting, like
Let us
crop
suppose SIP.
fields?
Let us suppose SIP detection is there.
Oh, yeah, ship detection. Yes, since there is that the SAR data is highly used in that. I think I'm not sure about because I'm not into ship detection because my expertise is mostly in crop and forestry.
Okay.
But label data in Google Earth Engine, I'm not sure. But if it is available in any public platform, you can directly import the labels directly here for that specific region, and you can work with that.
Because most of the problem is related to the ground truth, actually.
Yeah, that's true. That's true. Because ship tools for this particular ship detection, I don't know because I don't have much expertise in that domain. But for crop map and forest maps, there are a lot of maps. I mean, we can actually check if there are any data sets available here. So you can actually let's see. I mean, it just add a keyword shipping network. No, it's a ship. Let's say with the keyword ship, we'll see. Is there any data sets? Sorry, I think ship watch, vessel hours. There are, I think, no direct data sets available with her ship detection.
Okay, sir.
But yeah. Any other questions?
Okay, sir. Nice to
Okay.
explore this Google
Yes,
Earth Engine.
Varsha ma'am.
Yes, ma'am.
Yeah, Madhuri ma'am, you can ask question.
Yes, ma'am.
Yeah. Good evening, everybody. Yeah, thank you, sir, for the nice session. I'm very novice to this topic, but I would like to know the parameters VV, VH, HV, and H, those which are there. How, what is
Mhm.
the way to decide which one to take in this SAR?
Okay, that's an interesting question. So a quick one is okay. We can ask in a different way. So why these satellite
Yeah,
missions picked up between these two? Let's say how L-band picked up for HH, and while the Sentinel mission chose for VV. So this uh, is something like the mission's scientific objectives. The Sentinel-1 to be specific, is much more concentrated on agriculture domain. So for agriculture, let's say crop monitoring, for crops, a VVVH is much more sensitive, let's say for vertical structures, than HH.
Okay.
So if you are going for, let's say, soil moisture kind of studies, which may much more geophysical parameters rather than canopy parameters, then HH actually performs better than VV because it is much more sensitive to the surface parameters than vertically parameters. So in crudely, yeah, the polarization is sensitive to the orientation. So if it is V polarization, it's sensitive to the mostly vertically oriented structures like tree stems and all those crop parameters. And if it is horizontally polarized, mostly the surface parameters like soil moisture and other things. That's kind of one
Okay.
short answer. Yeah.
Okay. Okay. Thank you so much, sir.
Yeah, Madhuri ma'am, you can ask question.
Yes, ma'am.
Yeah.
Sir, thanks for this such informative session, first of all. My question is related to the, can you share the links, whatever you have shown, that will be helpful as a starting point to find out the programming using the Google Earth Engine? So is any
This,
specific tutorial or material where I can get to start the programming using Google Earth Engine?
you mean the codes I've used
Yeah,
in the
programming.
tutorial or the in general?
No, tutorial.
Yeah, these all the codes will be shared with all the participants, and I will actually give it to the whoever managing the session. So yeah, and also there are, like, I'll keep it in my GitHub repository. There, these app and these complex codes are directly available in my GitHub repository. So if you actually go there, so I'll share these links with you. Like, so there is this dual pole descriptor. Okay, there it is. So yes, here there is this repository. You can get these advanced scripts, which can where you can actually directly export to your Google Drive in geotiffs and CSVs and everything. So you can actually follow this. I'll upload everything, all this tutorial as a folder in this tutorial. So where you have already these JavaScripts, if you see this, so the entire script is available.
Okay, sir. Thank you, sir.
Sir, just one question. In your presentation, somewhere you mentioned that sea area or water look black.
Yes.
In SAR images, but its
Yes.
dielectric constant is greater.
High. Yes. So it should look bright, not dark, right? Yes, that's a very interesting observation. Yes, technically, the water should act as a mirror. It is a mirror for SAR in a way. But what is happening here? So that's why I kept this backscatter. So in specific to the water, it reflects almost entire energy back. Back in the sense in the forward direction instead of backward direction. So we are actually only collecting here. So in the backward direction, let's say if you have a sensor opposite to wherever you are sending, so you will get almost entire energy as a mirror. Yes, water should reflect almost entire energy back in the sense in a forward direction. So it means a forward scattering, we call it a specular reflection. So then back scattering. So there are like two phenomena. We only dealt with the back scatter, but there is a forward scattering. So if you, that is called mostly, that is used in bistatic radars when you have two sensors. So you have a transmitter and on the other side you have a receiver.
Okay.
Yeah.
Understood.
Yeah, thanks. Interesting question.
Yes, one more question I want to ask on behalf of our participants. How can we use SAR data for agriculture applications, especially in the context of Indian scenarios as we have small land holding? What specific database are available for free access and use online?
So I would say an Indian scenario is always a limiting condition for majority of the remote sensing methods because of this small farmland. I mean, for this in specific to agriculture, because we always have this pixel problem as an optical or the SAR, because the one pixel we are getting, let's say in the Sentinel case, is 5 by 20 meters. But typically our fields will be either less than that or you will get like 2-3 pixels per field. It is difficult in that case, but we do have some commercial data sets which provide high resolution, but again, they suffer from the speckle noise. But for small scale things, it's still a kind of a limitation, I would say. Even if you use a high resolution, let's say LOS2, same LOS2 with a fine beam dual pole mode, they will give you a data of roughly like 2-3 meters, roughly 3 meter data. You can actually see that I've mentioned here. There is limited availability, but there is LOS2 data available at a 3 meter resolution. But still, but agricultural for a small scale is always a challenge. So again, there will be this, because in SAR, to get rid of this speckle and to get a homogeneous area, and which is challenging, we have to average pixels or we have to filter pixels, where we lose the resolution of the SAR.
Okay.
Coming to the openly available datasets, yep, 2 years ago, ISRO announced their space policy, where all the ISRO datasets till now archive is available. You can even recently, last year, they launched EOS-04, which is a full polarimetric data, is available directly in Praniti. You can actually download that from that. It's free for all. There are processing tools, but they are not available on Google Earth Engine, but you can locally download them and just upload to Google Earth Engine for processing.
Okay. Thank you, sir.
Yeah.
Yeah, now it's time to express our heartfelt gratitude to our esteemed expert, Dr. Narayana Rao, sir, for his insightful presentation on SAR data and Google Earth Engine. Sir, we are deeply thankful for the time and expertise you have so generously shared with us. Your session has provided us with the valuable perspectives on the various aspects and applications of Geo-AI in working with SAR data on Google Earth Engine. Thank you for inspiring us and enriching our understanding of this cutting edge topic. Thank you once again. Thank you so much.
Thank you. Thank you all. Thanks for attending. Yeah. Thanks for inviting me. Thank you.
Yeah, thank you, sir. Digambar, sir. Dr. Ronnie, sir, you can share the screen and you can just test your system.
All right, thank you. So I
Hello.
presume you can hear me?
Yeah. Good morning, Ronnie. Sangeeta
Yeah.
here. Yeah, thank you so much for joining in. So, yeah, you can just share your screen so that testing can be done.
Yeah, on it. Do you see it?
Yeah, we can see.
Bhakti?
Yeah. You can change the slide once. Yeah. It is working properly. Prakash, sir, shall we start?
Yes,
Please start. Yeah.
Okay.
Hello. Please start, ma'am.
Yes, sir, yes, sir. We now move forward on session 8 of our program. It is an absolute privilege to have us with Dr. Ronnie Hans, a distinguished expert in the field of geo remote sensing area. Dr. Ronnie Hans received the diploma in computer science and PhD degree from TU Berlin, Germany in 2007 and 2014 respectively. He is a scientist at the Microwave and Radar Institute of the German Aerospace Center, DLR, where he leads the machine learning team in the signal processing group of the ASAR Technology Department. He served as a chair of the GRSS Image Analysis and Data Fusion IADF Technical Committee and editor of the GRSS e-newsletter. Currently, he is a co-chair of the ISPRS Working Group on Image Orientation and Sensor Fusion, editor-in-chief of the Geoscience and Remote Sensing Letter, co-organizer of the CVPR workshop Earth Vision 2017 to 2024, and the IGARSS tutorial on machine learning in remote sensing since 2017-2024. He has extensive experience in organizing remote sensing community competitions, serves as the GRSS representative within SpaceNet, and was the technical lead of the SpaceNet 8 challenges. It's a great honor to have such an eminent personality with us. A warm welcome, sir, to you. Yeah. Dr. Ronnie will lead us through the next session, and we are excited to gain valuable insight from his expertise. Let's warmly welcome Dr. Ronnie, sir. As we begin this session, over to you, sir.
Yeah, thank you very much for this very kind introduction.
Yeah.
I'm sorry that you didn't had any break, but you jumping directly from one topic to the next one. Luckily, many of the images or many of the data I will talk about is also SAR, so it's not a complete change. So there's a little bit of smooth transition, but we are changing a little bit from like basic feature extraction, automatic processing in a system like the Google Earth Engine to a more like method-driven view, how we can actually analyze any kind of remote sensing data, but in particular photometric SAR images with a particular method. And here I choose random forests, so not deep learning, not neural networks. I will explain a little bit at the end why. But random forest. And what I want to do is I want to start a little bit with an introduction to what are random forests, why are they nice, why they are still meaningful to be discussed even in the era of deep learning, what kind of properties do they have, and then we come to the general topic of like how can we stack random forests, what does it actually mean, what is stacking, and why does it make sense. I think I will probably talk around 60-70 minutes, and that will leave some room for discussion at the end. So maybe you wonder why I choose random forests, although nowadays nearly everybody is doing deep learning. It's not because I don't believe in deep learning, right? I mean, deep learning has proven itself over and over again, not just in natural language processing, autonomous driving, but also in applications that are more of concern to us. There are a lot of remote sensing companies, research institutes that are solely based on deep learning applied to Earth observation data. So it's obviously working. But from a scientific point of view, I don't like a monoculture, right? We would not have deep learning if we would believe in a monoculture in science. Because neural networks were considered dead for quite a while until they were revived by deep learning. But on the other hand, I also believe that as a scientist and also as an engineer, you should have like a toolbox, and you should be able to choose the right tool for the right problem. And deep learning is a very powerful tool, but it's not the right tool for every problem that is out there. In particular, in remote sensing and Earth observation, there are still plenty of problems where I believe a strong traditional learning method, like, for example, random forest, will outperform deep learning because the problem is structured in a certain way. So let's start a little bit with what are random forests, and I hope I don't bore you too much with this introduction, but those basics are important to understand the advanced concepts that are coming later on. So a random forest is nothing else than an ensemble, a set of decision trees. Usually it's just really binary tree. So you have a set of nodes and each node has only two children node. And what you could imagine is that those nodes are nothing else than splitting your space into two half spaces, right? So if you have here this two-dimensional space, so this is just for the visualization purposes, of course, usually our spaces, our feature spaces, data spaces have a much higher dimensionality, but those are difficult to plot. So let's assume you only have two dimensions, for example, two features that we have extracted from our data. You had heard before about dual problematic data, right? Like Sentinel-1, for example. So this could be the backscatter in HH, and this could be the backscatter in HV. And let's say now you have two classes, for example, forest and non-forest, or water and not water, or something like this. One class is denoted by the blue color and the other one by the red color. Now, when we look at the decision tree, this single node here, the so-called root node, is basically describing the full space and all the samples that are in. And now it's making a binary decision. That basically means we are selecting one of the dimensions, put a threshold there, and now every sample that has a value in this dimension that is smaller than this threshold, it would go to the left child node. And if it's larger, it goes to the right child node. So this would be exactly those two child nodes over here, right? You see here on the left-hand side, we have more red than blue, right? So this is, I showed this here with this small histogram, what the class distribution is. On the right side, blue is a little bit more dominant, but it's more balanced. And now we just continue with this. So now we take one of those half spaces, we choose another dimension, and we make another split. So again, now we choose this left half space, we put another threshold in there, and we made another split. And now we really just continue recursively until we meet a certain stopping criteria. For example, we might say we don't want to go deeper than 1, 2, 3, 4, 5 levels. Or we can also say we stop as soon as a current node has only a certain minimum number of samples. So if there's only one sample, you can't split further, but you might actually stop a little bit earlier where you have like 2 or 3 samples in order to still be able to have some kind of robust estimate of the target variable. But other than that, we just continue recursively splitting until we have processed all the data. All the spaces have been split until we met a stopping criteria. So this is a decision tree, right? Decision trees are very well understood. They're very easy to implement. It's what you learn like second term in your bachelor if you study computer science or something like that. It's a very well-established data structure with a lot of variations around and very, very efficient. And it is very efficient because you have very simple decisions that you need to make at every node, right? So each node here just taking one dimension of a sample, compares it with a threshold, right? And then assigns a binary value left or right child node. And although you might have a large number of nodes in the overall tree, if you would enter a new sample into this decision tree, it would follow only one path, right? So that means only a very small number of those binary decisions need to be made. And just to clarify the terminology again a little bit, so this top one here is a root node. The nodes here at the bottom where the splitting stopped, it's called leaf nodes and terminal nodes. You can tell this was designed by computer scientists that don't go out very much. The root node is on top and the leaves on the bottom. Usually, the forest, the tree grows in the other direction. But anyway, and then those nodes inside of the tree here, they are called internal nodes or split nodes. So they are making decisions, while in the leaf or in the terminal nodes, you would save an estimate of the target variable based on the samples that have reached this leaf. So for example, here we have a classification problem. We want to know is it a red sample or a blue sample. So we would simply observe what kind of samples have reached a certain node, right? So for example, in this one, there's only blue, so we would only assign the blue class or 100% of the blue class to this leaf node. So it's a very, very simple mechanism, a very simple classifier, but the decision boundaries you can build with this are actually quite complex already. So you see here, again, a toy example. This blue line here is now the decision boundary. The decision boundary is where the decision would switch, right? So if you're on this side of the decision boundary, you would say it's a red sample. If you're on the other hand, it's a blue sample. It's already, non-convex, piecewise linear, even piecewise axis aligned, but in total it's non-linear or non-convex, even disconnected, right? I can single out different areas. And the other thing what I can do is within those cells, I can actually assign a posterior, right? So that's what I try to illustrate here with this kind of shaded color, right? So in here, the decision tree would tell you, I'm not quite certain whether it's red or blue. It's, 66% blue and 33% it's red. While out here you would say it's 100% red, and here you would say it's 100% blue. So it's a very simple method, but is able to solve actually quite complicated tasks already. So far we only talked about very simple node tests, right? A node test is telling you whether a sample should go to the left or to the right child node, right? We just talked about using one of the dimensions and put a threshold there, and then everything that is left of the threshold goes to the left child node. Everything that is larger than the threshold goes to the right child node. But you're not bound to that. Actually, you can be quite creative. So for example, what you can also do is you could have an interval and saying with two thresholds, everything that is inside of this interval goes to the left child node, and everything that is outside goes to the right child node. Also, you don't need to have axis-aligned splits. You can have linear splits, right? So then your hyperplane would not be axis-aligned anymore, right? It would be a combination of the two features. But then it stays the same. You can say everything on the left or everything on the right goes to the left and to the right child node, or same with the interval. We're also not bound to linear split decisions. We can have non-linear decisions, right? We can say, well, everything inside of this conic section here goes to the left child node. Everything outside goes to the other one. And again, you could build like this interval idea also with non-linear functions. So you would have this donut shape here where you say, well, everything that is on the donut, it goes to the left child node. And then what is inside of this hole and outside of the donut goes to the right child node. So you can be very, very creative, and we will see another example a little bit later on where you can build very specific test functions to very specific data that you might encounter. So what are the advantages of decision trees? Well, the first one is heterogeneous data is no problem. So if you think about data fusion, and you might have radar data, you might have hyperspectral data, you might have depth information, you might have other variables, maybe even categorical variables. No? For example, right now we have global land cover, land use products that you could use in your decision system as an input. For most classifiers, like a neural network, support vector machines, this heterogeneous input is quite challenging. They can't really deal with that, because what they usually do is to have a numerical weight vector, right? So for support vector machines, that would be the support vectors where you compute the scalar product. For neural networks, you would have the weight vector or the kernel, if you talk about convolutional networks. And then they would multiply those weights with all your input data and then sum everything up. So this means you're suddenly summing over very different variables that live on very different scales and have very different properties. No? Some of them might not even be numerical. They might be categorical, and then a multiplication and adding doesn't make any sense. For a decision tree, it doesn't really matter, because at every internal node, you only pick one dimension, and then you do something with this feature, right? And you can select what you do with this feature depending on what it is. So heterogeneous data is no problem for decision trees. For the same reason, the curse of dimensionality or the hue phenomenon is also not a problem. Usually, you would expect if you're adding features to your decision system the predictive power of the system gets better because it has access to more information. However, this is only true to some extent. So if you keep adding features and they are informative, let's assume that, then the performance goes first up and then it decreases. And the reason is that for a data-driven system, like a support vector machine, like a neural network, the amount of training data that you need to train the system increases exponentially with the input dimension, right? So if I go from 1 dimension to 2 dimensions, I not just need twice the amount of data, well, there it's still twice, but if we go from 2 to 3, you know, then it's not just doubling the amount of training data that we need, it's actually to the power of 2 that we need. For random forests and for decision trees, this is not the case, because again, every node just picks 1 dimension and is doing something like with this dimension. Whether this dimension is picked up 1 out of 10 or 1 out of 100 or 1 out of 1,000, it does not really matter much for the decision trees. It's very, very efficient because every node is just making a very simple decision, applies a very simple function to your query, to your sample. And you don't have many of those that needs to be applied to a sample, because a sample only follows a single path through the tree, and the length of this path is basically the tree height. So if you have a tree of height of 10, then you need to apply around 10 tests, very simple binary tests to your data, and then you already have your decision. So this is quite efficient. As I said, it's easy to implement. It's what you learn first. It's one of the first basic data structures that you learn when you study computer science. There's a lot of code around, and they're also quite optimized. It's also easy to interpret, right? So deep learning is very often criticized of being a black box model. A decision tree is just a collection of if-then-else rules, right? If this feature, if the value in this feature dimension is smaller than the threshold, then you do this. Otherwise, you do that. So it's really just if-then-else. The bigger the tree, the more complicated those rules are. But any kind of decision tree you can write down as a set of if-then-else rules. So you could print down a decision tree in a human readable form. And they're really good understood. We have decision trees for nearly half a century now. There's a lot of practical considerations that make them more efficient or more robust. And also from a theoretical point of view, they're very well understood. We know exactly what kind of predictions they are making, what kind of statistical properties they have, and so on. So now the question is, of course, when the decision trees are so great, why are we not using them that much? So they do have a couple of disadvantages. The first one is you can optimize them. We will see a little bit later how to do that, but it's a greedy optimization. This means you're making a local decision what kind of optimization you should do. And then you have this chain of locally optimal decision, and there's no guarantee that this chain of locally optimal decision is also globally optimal. So we can't really guarantee that. The other problem is that if there is a true solution to your problem, it might not be part of the model class that a single decision tree can create. So for example, if we have those axis-aligned node tests, you can't really learn a nonlinear function by that. You can approximate it, and if you have a lot of data, you can approximate it quite well, but you can't really get it. No? So you can't really create a nonlinear function based on piecewise linear functions. Overfitting is a really big problem for decision trees. It's really easy that your decision tree is just memorizing your data. You just keep splitting your data until there's only one single sample left in a leaf node. And that basically means you have created a lookup table for your data, right? It's completely overfitted. Has 0 error on the training data, probably a very large error on test data. And the other problem is that the capacity of the model, the capacity of the decision tree, what the decision tree can actually learn, depends on how much data you have. If you only have a few samples, you can only create very small trees. right? There's no way around this. You can't create a really big tree if you only have 100 samples. You could imagine that if the tree is working very well, each node would split the data in two halves, right? 50% go to the left child node, 50% go to the right child node. So this means if you start with 100 samples in your training data, then it's 100 at the root node, then it's 50 samples, 25 samples, 12 samples, 6 samples, 3 samples, and then you're basically done, right? So much more than 6 questions, right? More than 6 of those binary tests you can't apply to your data. And this might not be enough to solve very complicated tasks. And actually, this was the main idea for random forests. What random forests are doing is just creating many of those trees, because the idea was that, well, we want to compute more features, we want to compute more of those binary questions, but we can't do this in a single tree because we don't have enough data. But what we can do is we can create multiple trees. Then we can still compute more features and ask more questions. On the other hand, many samples is also a little bit a problem, because if you don't artificially restrict the growth of the tree, it will keep growing if you feed it more data. This is in contrast to neural networks, for example. The size of the neural network is predefined, right? You're just adjusting the weights, but it's not growing, at least not in the standard way to train a neural network. It's not growing during training. It doesn't matter for the neural network if you train it on a single sample or 1 billion samples. So the size of the neural network stays the same. It's different for a decision tree. A decision tree, if you not artificially restrict the growth, it will continue to grow if you feed it more data. And it will grow exponentially, right? If you think about binary decision trees, the number of nodes doubles for every tree level, right? At the 0 level, for the root node, you have only 1, then it's 2, then it's 4, then it's 8, and so on, right? So it doubles at every tree level. This means it can grow out of your memory capacity quite quickly if you have a lot of data. So, of course, we want to keep most of those advantages and getting rid of the disadvantages, and the solution to that is, of course, random forests. And random forests are not doing anything magical. The only thing they do is they create multiple of those decision trees. That's it. Right? There's nothing else. There's no other optimization going on or whatsoever. The basic concept of random forest is simply create multiple of those decision trees. Nothing else. So why does this make sense? So this is again the toy example from before, but this time I did this partitioning in a slightly different way, right? So I picked I didn't start with x1, I started with x2. I put the thresholds maybe somewhere else, and so on. In this way, I get 3 different partitionings of my input space, right? It's 3 different decision trees. They are all trained on the same data in this example, just with a little bit of randomization. And what I'm getting out is 3 times a similar solution. So for example, this part down here, it's always classified as being the red class. No? Here, here, and also here. This part over here, it's always classified as being the blue class, no? In all 3 of them. In other parts, we see more a variation. And now what random forests are doing is to take those multiple decision trees and just combine them. Simple average. So if I would have only 1 tree, the result would like this. It would just be my input tree. If I have 2 trees, it looks like that. And if I use all the 3 trees, then it looks like this. So now the partitioning is actually much more fine-grained, right? It has a higher resolution, just because those individual partitionings are not really overlapping to 100%. And I also get a much more fine-grained estimation of the class posterior distribution down here. So this is really just all what random forests are doing. Create multiple decision trees with a little bit of randomization so that we are getting different trees, and then just combine them either by you can have a voting structure that, for example, every tree votes for a certain class, but you can also just average the class posterior that each tree is giving you. There are different ways to fuse it, but those are the 2 most common ones. So just to summarize, what are random forests? It's really just a set of decision trees. Each tree is generated from the training data. independent of the other trees, right? So there's you can grow them in parallel. It's no problem. You need to have a little bit of randomness in one way or another to make sure that you're really getting different trees, not like 100 copies of the same tree. And then you need to fuse the different outcomes from the individual trees, for example, by averaging or by voting. So random forests have a couple of advantages. For example, you can mathematically prove that the output of the average of a set of decision trees or a set of models is better than randomly picking one. Right? So if you would only train one model, you could imagine that as randomly picking one of those models. And on average, the random forest, the whole ensemble will perform significantly better than any of those individual models. Sometimes your models, no matter what it is, they depend on the initialization, right? For example, for neural networks, they depend quite a bit on how they are initialized. Support vector machines, not so much, but also there's a little bit of randomness involved. So there's a little bit of risk that you're just unlucky and you pick a model in initialization that is really bad and you end up in a bad local minima, right? Now, if you're creating multiple models, this risk is reduced, right? So maybe if you only create one, you're getting stuck in a local minima. But if you create 1,000 models, right, this risk that all of them are stuck in a bad local minima is quite small. Most of them probably will find a good solution. And then you're averaging over everything. So those weak models that are getting stuck in the bad local minima, they will be averaged out. This problem that we had before, that the true solution might not be part of the model space, is also gone, because now we are averaging over different models. So with this, you can actually get nonlinear decision boundaries, even if the individual ones are linear. And all of those advantages make random forests really, really strong. And they were on the rise until maybe 2010, 14, and then deep learning took over. Now, if you read the literature, you will see a lot of names, and that's a little bit something that I don't like about the random forest community. They have the tendency of changing a tiny detail in the overall random forest framework and then give it a completely different name. But as long as they have trees or forests in it, it's mostly the same concept. So back decision trees, randomized trees, decision forest, ERT stands for extremely randomized trees, PERT stands for perfectly extremely randomized trees. Then we have rotation forest, canonical correlation forest, Huff forest, and so on. All of them is the same concept. They are different in some details. Some details are only a little bit different, others are a little bit more different, but at the end of the day, they are all following this concept of having different decision trees with a little bit of randomness created independent of each other, and then they are combined together. So for random forests, there are a couple of key questions, and we won't have time to go through all of them. Only through some of them I want to address today. And the first one is, well, what kind of node tests can we do? What kind of binary questions can we ask to the data? So when I started my PhD, my task was to write a classification system, a semantic segmentation system for radar data without knowing the actual task. So during the design of my processing chain, I only knew I want to do some kind of maps from some kind of radar data, but I wouldn't know during the design of the framework what kind of radar data. Is it fully polymetric? Is it dual pole? Is it single channel? I also don't know what kind of classification problem I'm supposed to solve. Might be forest non-forest maps or land use land cover maps, building footprint detection or something like that. This is then only known when I train the system, right? And this was before the era of deep learning, right? So today it's kind of always the case, right? We have our deep neural network, we put our data in, we train it with the reference data that we have, and then we have our outcome. Back then, what you would usually do would be a very long processing pipeline that is, reading your data, extracting some kind of features from your data, maybe doing feature selection. Then you would feed those selected features into a classifier. The classifier would give you an outcome, and then you would post-process this outcome a little bit. And for each of those steps, there are like whole research areas around them, right? So feature extraction, feature selection, those are like two big areas of research back then. All of this kind of vanished with deep learning, but back then it was still the case. So I was supposed to solve this a little bit, and my idea was that, well, since I don't really know the classification task this system will be trained on during the design of the system, I can't really say, feature A is really good and feature B is really good, right? So my approach to solve that was, well, if I can't decide which feature is good up front, I just compute all of them, and I want that the classifier is taking care of that, right? The classifier should select which feature is good. I just compute all of them. So given a fully programmatic SAR image, I would compute a lot of different features, some of them fully programmatic, some of them only based on a single programmatic channel. You can also convert a programmatic image into a pseudo color image, then you can compute color features. You can also, of course, compute a grayscale image based on that, and you can compute grayscale features, and even for binary features, you can do that. So I just computed a whole bunch of features. So this means if I want to decide what kind of class is shown here in the center, I was using a spatial neighborhood, usually smaller than that one here, but I wanted that you can see a little bit what's going on. And then I had this whole bunch of features. And now that is like one sample, right? So now I want to, based on this information, I want to know what is the class here in the center. So what the node test was doing in my random forest back then was it would take such a hypercube and would select one of the features randomly. So from all of those hundreds of features that I've computed, take one out randomly. And then within this one feature, I just select two regions and I compute, for example, the difference, right? So maybe I take the center pixel of this region and the center pixel of this region and just compute the difference. And that means I have a scalar value. So what I have is this projection from this hypercube, right? So this three-dimensional tensor that has spatial information and a lot of feature information, I projected this into a scalar value. So this means I go from this three-dimensional cubes to a one-dimensional space, and in this one-dimensional space, I can put my threshold, and then I say, well, if the computed feature value of a sample is smaller than this threshold, you go to the left child node. Otherwise, you go to the right child node. And the thing is, you can be really creative here, right? So you're completely free what kind of features you're computing. If I designed back then nearly 400 different features, but if a feature that you know in your application is not included there and you think it's meaningful, you can just throw it in. It doesn't really matter. Also for this spatial projections, you can be very creative. What I tried back then was like 3 different groups. The most simplest one would take a certain region within a patch, applies an operator to that. This operator would just give me some kind of pixel within this region. So for example, the center pixel, or you can sum up all the pixel values in this region, or you can take the minimum value or the maximum value, right? And then you compare it with a reference value. So this is basically like an absolute feature that you would compute, right? So using this one, you would do something like all samples where a certain feature is large go to the left child node, and where it's small, they go to the right child node. The second group here, they would compute the difference. So I would extract 2 regions in my patch. Again, I apply an operator to these 2 regions. For example, I take the center pixel of the 2 regions, and then I just compute the difference between those 2. So what they are doing is they're computing a relative feature, right? Like a gradient. So within a feature map, like for example this one, they would say, well, if there's an edge in this feature map, then you go left, and otherwise you go right. And you can do even more complicated stuff, like the difference of 2 differences, something like that. And that worked very well. So here you see a fully programmatic radar image over the German Aerospace Center. So this one here is the campus of the German Aerospace Center. Here, this one here is an airport. This one here is a small town, the city of Gilching, close to Munich. Here we see some forest area, and here's some grassland and some agricultural land. I had reference data for that, so I had people sitting down and labeling this, and then I trained my random forest on this data and applied it to test regions within this. So here you see the result, and it worked quite well, right? So I got an accuracy of around 90%. Roads are difficult because roads are very tiny, in particular here in the city. So there we have only like a mediocre accuracy, but the rest is actually quite good, apart from smaller problems. But then I noticed, well, it's kind of nice because now this feature selection is included already in my classifier. This is nice. I still need to pre-compute those features though. So before I can do my classification, I need to spend a lot of time, computation time, to compute all the features. And then I need to hold all of those features in memory, right? So if I have 100 features, that basically means I have like 100 versions of my radar image in memory, and I need to hold it there. So this is not really really nice. No? So if you have a lot of data, a lot of radar images that we might want to analyze or we want to train the system on, you're running out of memory quite quickly, and then you need to load stuff from the disk. Then it's getting slow and so on. But when I was looking at this formulation I had here, I noticed that, well, actually, I'm writing always minus here because when I developed this, I had scalar features, right, that I had computed. Basically grayscale images, but I can easily generalize this to a distance, right? So I can say, well, instead of pixel 1 minus pixel 2, I can say, well, apply a distance measure based on pixel 1 and pixel 2. And this distance measure can vary depending on what kind of data I have. So if I have only grayscale images or feature images, then it might be a very simple signed or absolute difference of those scalar values, right? Then my operator that I applied to this random region in a patch would give me a pixel. In this case, it would be a scalar value. And then my distance would just be, a minus b, something like this. But if I have something else, for example, an RGB image, a color image, then, well, my operator still goes from a small image region to a pixel value, but in this case, it's not a scalar value, it's a 3-element vector, right? The RGB vector, for example. And my distance measure then is just defined over the space of 3D vectors, right? So it's taking two RGB vectors or whatever color space you want to use, and then it's giving me the distance between those two. It could, for example, be the Euclidean distance in some color space, or maybe also just the absolute difference in a particular component of this vector. And if you have radar images, so maybe your radar image is represented by the polarimetric covariance matrix. So in every pixel, you have a matrix, a Hermitian matrix. Well, my operator still gives me a pixel, a single pixel in this type. In this case, it would be a matrix, and then my distance measure would be defined over the space of matrices. Right, so it takes two matrices, gives me a scalar. And for polarimetric SAR images, there are quite some distance measures that we can actually take. They are directly defined over the space of Hermitian matrices, so that works quite nicely. And this means now I don't need to extract features anymore. I can directly feed my data into this random forest. The random forest will apply this kind of setup on the data itself and compute the features that it wants on its own. And then I tried this out on the example from before. So this is the reference data. Here's the second row, what we achieved before. And this is what we achieve now. So we lose a little bit of performance, but actually not much. But the advantage is that here we really needed to keep hundreds of feature images in memory, and we needed to pre-compute them, while here we don't need to do that. So just to summarize this idea, the goal is really you want to make a decision about the center pixel here. The first thing you do is you take two random regions in this patch. So you use a patch around the center pixel. You take two random regions in this patch. You select or compute a pixel value in those regions, so maybe a minimum value or the center pixel, or you average all the pixel values, whatever you want to do. And then you apply a distance measure to those two pixel values. So some kind of distance or similarity metric taking this one, this pixel, and this pixel, for example. That gives you a scalar value, right? So the distance between those two, and those you can compare to a threshold, and then you need to define a split point there. This can be applied to any kind of data what you have. Can be radar images, single pole, multi-pole, dual pole, can be hyperspectral data, can be categorical data, and so on. And this will become later important when we talk about stacking. It learns the features implicitly directly from the data, right? So you can work directly on the raw data. There's no need to pre-compute features. But if you have an idea that in your specific application, a specific feature is of importance, you can also include it additional to the original data, and then the random forest can use it. So what we didn't talk about yet was how to select this threshold, right? So far I only explained how to project a patch, a data patch like this to a scalar value, right? But now we still need to compare the scalar value to a threshold to decide whether this sample goes left or right in your decision tree. So the easiest thing what you can do is you can pick it randomly. So let's assume this one here is our data distribution. So this blue curve here is like a histogram over all the projected values that we have at a specific route. At a specific node. What you can do is you can pick a value randomly between the minimum and the maximum value of this data distribution. So this red one here is the probability of picking this particular value as a threshold. That's the easiest thing you can do. No? There's like no optimization going on whatsoever. What you see down here is the performance of random forests on a particular task that was done in where the random forest was trained using this kind of uniform splitting. On the x-axis, you have the number of trees, and on the y-axis, you have the height, the maximum height of the trees. And blue means it's not solving the task; it's very poor performance, and red means it's perfect performance. No? So it's going from 0% accuracy to 100% accuracy. And what you can see is, well, the more trees I have and the deeper the trees get, the better the performance gets, right? And I need quite a lot of trees and also quite high trees in order to get anything that is decent, right? So orange is around 75%. Another version of picking a split point randomly that is a little bit more optimized is not using a uniform distribution between the minimum and the maximum, but we use a Gaussian distribution where the center value of the Gaussian is the mean of your data distribution. So the mean value of this data distribution is somewhere here, and that's where we place our Gaussian distribution, and the standard deviation is the standard deviation of your data distribution. So this is a little bit more optimized because here the split points will be centered somewhere here, right, where the center of the data is as well, right? So you're having more balanced splits. If you do a uniform distribution, you might end up with a split that is here, that is only splitting, you know, like 5% to the data to the left child node and 95% to the right child node. Here, it's more prone to be 50-50. Not always. You also have a small probability of having a split point here, but mostly it will be somewhere here in the middle, and then it splits it more evenly. And you can see this in the performance, right? So now it's much more orange, and you know the maximum also goes more to red than in this case here. So this means I need less number of trees and mostly deeper, less deep trees. No? So here with a maximum tree height of 10, I'm already in the orange space, right? So around 70 to 80% accuracy. Where here with 10, I was still in the bluish, greenish, yellowish, which is you know around 50% accuracy. But we can do even more. And the most common way is that you take the reference data into account that you have, and you're trying to create child nodes that are as pure as possible regarding the reference data. So what you would like to have is that, let's say you have a binary classification problems, only two classes, A and B, that all the samples of class A going to the left child node and all the samples of class B are going to the right child node. No, that should be your goal. So for this, you need to have some kind of measure of impurity, but let's assume for a moment that you have that. then what you can very easily do is you can compute the impurity of the parent node, the impurity of the left child node, and the impurity of the right child node, and you just compute the difference, right? So you want to make this as big as possible. And of course, you want to weight this a little bit, because if you're only splitting like one sample away, this sample will be very pure. It only has one class, but you don't want this type of splits. So that's why you're weighting this with the leaf side node of the left and the right child node. So what can be used as a measure of impurity? There are different things around. They're not so different in their performance. The most easiest to understand is the entropy. So you just take the class distribution in a node and you compute the entropy of this class distribution. So if you have a uniform class distribution, the entropy will be very large. And if you have only a single class, the entropy will be 0. So this can be your measure of impurity of your node. You plug it into this optimization scheme, and then you're choosing the threshold that is optimizing this. So this black line here is the data distribution that we had seen before. Those colored lines here are the different class likelihoods, right? So we have 5 different classes. And the green line here is the function of the impurity, right? And then you choose the one where you have the biggest drop of impurity, right? Where we create child nodes that are as large as possible, as balanced as possible, but also as pure as possible. And then you select this as your threshold, and that's then a very strongly optimized threshold. The other thing we need to talk about is a little bit how to select node tests. So far we have talked about how to create them, right? So how to go from a sample to a scalar value that we then can compare with a threshold. And we also have just discussed how to select and optimize this threshold. But what we usually want to do in a decision tree is that every node is not just creating one of those test functions, but multiple candidates. And then from those multiple candidates, we take the best one. Now you can ask, okay, how many candidates should I create? And usually, traditionally, people use something like the square root of the dimension of your data. So if you have a feature vector of 10 components, you would use the square root of 10, which is like 3, rounded. Well, if your feature dimensionality is very large, and if you do this, the spatial projections, basically it's virtually infinite, right? Because there's a lot of different variations that you can compute. This doesn't really make sense. So here I would just go with a predefined value, which is a little bit of compromise between compute power and optimization. And optimization also is a trade-off between very strong trees and very correlated trees, right? And very correlated trees we don't want. We don't want to have 100 times the same tree. We want to have a little bit of randomization going on. So the goal is not to find the overall best test that you can get. The goal is get a good one, right? But it doesn't need to be the best. In my experience, even if you already just use 2, performance already gets much, much better. Because if you completely randomly pick only one test, there's quite a chance that this test is just not performing very well. The probability that you pick a second one that is also not performing very well is quite low, actually. And then, of course, if you go higher, the probability that you pick a very good one is just increasing. Well, and then you select the best of those and reject all the others, and this is then the one that you use. And with this one, you continue. So what you see here is when we don't do any kind of optimization, so we just select the split point uniformly. Here we use the median of our data that is leading to very balanced trees, right? Because the median is the split point where you divide your data exactly in 50-50%. And then this one here is taking the reference data into account to find an optimized split point. And then the number of candidates is 1. And what you can see is, right, this one was not really good, right? We needed a lot of deep trees to get something that is around 75% accuracy. The median is already much better, right? We need much more shallower trees to reach a good performance. And if you optimize it even more, taking the reference data into account, then we are, with a lot of trees that are also deep, we are actually getting something about 85% accuracy. So results get better the more we optimize, but also the computational power and the time that we need is also getting higher, right? So here we just need to select a random value that's super fast. Here we need to compute the median. This is involving sorting. So this is at least linear logarithmic time complexity. And here we need to evaluate several split points, right? Depending on how many we evaluate here, this can be computationally quite expensive. Now, these are the results when we use not just one candidate, but 10 or even 100. And what you can see is that performance gets much, much better, right? But also, even if you have a very weak split point optimization, if you just create 10 of those and then select the best one from there, results are actually quite good. Not as good maybe as those, at least for very shallow trees, right? But with a decent tree, we already have a quite good performance. And right, if you increase the number even more, they're basically not distinguishing anymore. So we actually have kind of a choice to make 100 very random and very simple tests, right? Or a few very optimized tests. Those are basically the two choices that you have, lead to a very similar performance. All right, and the last point I want to briefly discuss is one big advantage of random forest, and this is how we can interpret the results. And one thing I really like about random forest is we can visualize them very nicely, and we can actually learn something very interesting about the random forest and also about the problem that we're trying to solve. So a while back, we programmed a little tool where you can just load a random forest. It's visualized as this set of dots. So every dot here is one tree in the forest. The position of those dots is based on the correlation of the trees. So if two trees are making very similar decisions, they are put close together. And if they're making very dissimilar decisions, they are placed further apart. And then you can select one of those trees and just visualize it. The length of those branches depends a little bit on how much data is in a branch, right? So if it's just a branch where only a few samples are, then it's very tiny, right? So we see this here. So maybe here only maybe 5% of the data went in this direction, where 95 went in this direction, right? So this is why this branch is much longer and thicker and also goes more straight. And then the leaf color is actually variable. And we will see this in a minute. We implemented two different choices. Either you can visualize the classes, right? Every class has a color and you can visualize that. Or you can visualize the purity of the leaves. That's what you see here. Green means it's very pure. So this green leaf nodes, they contain samples of mostly only a single class. And red means they are very impure. So they contain samples of multiple classes. And the size of the leaves show how much data is in them. So by doing this, just by looking at those visualizations, you can actually already learn something about the parameter setting and whether it's good or not. So if we optimize the split point on the median, we get a tree like this. It's very balanced, right? So every split splits the data into 50%, right? 50% go left, 50% go right. And then again, 50 left, 50 right, and so on. So it's very much balanced. It's very, we don't need a deep tree by doing that because we're always splitting the data in half in every decision. And it's very nicely balanced. On the other hand, here we have a tree that was optimized by just selecting the split point randomly, right, with this uniform distribution. And what you can see is it's extremely unbalanced. You have this long trunk, and I'm not sure whether it's getting clear over Zoom, but if you look closely, there are like tiny branches here, and here, and here, and here. So this means at those branches, a very marginal portion of your data went to one child node, maybe just like 1% or just 0.5% of your data went to the left child node. And all the rest of your data went to the other child node. So basically, this means you ask a very stupid question, right? You computed a feature that is basically meaningless because all the samples, nearly all the samples in this node, react to this question in the very same way. That's why you're getting those very imbalanced split decisions. And you can see that just by looking at the tree, right? So you see a tree that has this very long trunk, then you know, oh, this is a very imbalanced tree. I need to increase a little bit the optimization of my split point. Maybe I don't do it uniformly, maybe I do it based on the Gaussian, or maybe I include the median, or maybe I include like the reference data and I optimize that, but I need to do something in order to get a more balanced tree. The other thing I mentioned is that you can visualize either the class ID via colors in the leaf nodes. So here the different colors correspond to different classes. So there are 5 classes in total. And here it's the purity that is visualized. Green means it's a very pure leaf containing only samples of one class, and red means it's very impure. And if you have trees like this, you actually learn about your problem that is very easy to solve. Why is that? Well, you have very big leaves, right? You have 5 classes and you have 5 big leaves. So big leaves mean the majority of the data is there. And they're also very pure, right? So I have 5 classes, I have 5 major trees or sub-branches in my tree, and they're very pure. So this means it's a very simple problem to solve. If you look at it, basically after I make one question here, and I make one question here, and I already distinguish the 2 green classes from each other, right? There's only dark green over here and only light green over here. So by asking only like 2 questions, I can distinguish those 2 classes. By asking only one question, I can distinguish the cyan and the red class from the other classes. The blue class is a little bit more complicated, apparently, right? The blue class was the road class, if you remember from before. So this is a little bit more complicated, but the others are actually quite easy to distinguish. So you're not just learning something about how you should optimize the hyperparameters of your random forest, you also learn something about the problem at hand. Okay, and that brings me slowly to the end of the presentation. We wanted to talk about stacking random forests, right? And now I have all the requirements, everything that you need to understand so that I can explain what stacking is. So this is what we have talked so far about. We have a random forest, we have our input data, right? Might be a pulsar image that we feed to the random forest. We have the reference data that we use for training, and what the random forest is giving us is a class posterior distribution, right? So in this case, we had 5 classes, so I get a probability vector with 5 entries, and that's just what I visualized here. And then if I want to have this kind of label map, I just take for every pixel the class with the maximum probability, and that's how I get my semantic map. So this is what we did so far. Now what stacking is doing, or what stacked random forest is doing, is they add another random forest that, again, is using the input image and the reference data to train it. But as additional feature, it's also using the prediction of the first random forest. And you can do that very easily because you know right now that heterogeneous data is no problem for decision trees, right? With heterogeneous data, I mean, here we have a pulsar image. So in every pixel, we might have a 3 by 3 complex valued matrix, right? The polymetric covariance matrix in every pixel. For this data here, we have in every pixel a 5-dimensional vector that is representing the probability distribution over the classes. Those are 2 very different things. It does not make much sense to just, compute a scalar product between, any kind of weight vector and those 2 things together. It doesn't really make sense. You would need to make a lot of normalization because the values in this polymetric data are quite different from the values you get in your posterior. So for example, this one is always between 0 and 1, right? In your pulsar image, you can have easily values that go up to a couple of thousands. So it would be very complicated for neural networks or support vector machines. For random forest, for decision trees, no problem. If it randomly picks the radar image, then it's applying distance measures for pixels in the radar image. If it randomly picks the probability distribution, it applies the distance measure that is suitable for the probability distributions. All right, but why does it make sense? So why is this a good idea to do that? Well, this first random forest here, it will make mistakes. It will learn something that is just not true. Maybe it didn't have enough data to really learn it correctly. One typical example for this type of radar image is double bounds. Double bounce, you have a lot of in a city. Double bounce is when the radar wave is reflected twice, one on the ground, one on the object, and then it goes back, or the other way around. So you have this a lot in the city, because there you have a lot of buildings, and if they're oriented in the right way towards the sensor, you get this double bounce very easily. But you also have it in the forest, on the tree stems. So the double bounce is then on the soil, and then on the trunk of the tree, and then it goes back to the sensor. So sometimes you have double bounce in the forest, but mostly you have it in the city. So what this random forest might learn is, oh, there is double bounce, it's city. I have mostly seen that for city, sometimes in the forest, but mostly for city. So I will decide it's city. So now the second random forest will see, oh, the first random forest said this is city. And I also see that it's double bounce, so probably that is why. But I also see it's just a few pixels, maybe only 1 pixel, surrounded by forest. And this is something I never see in my training data. I never see a single city pixel surrounded by forest. Whenever this situation is happening in my training data, this city pixel is actually a false classification, and it's actually a forest. So the second random forest here can correct this type of systematic errors the first random forest is doing. And now we can just continue, right? Now we just continue. We add a third one and a fourth one. And again, we are just taking the input image and the output of the previous random forest, right? And then we just train it sequentially. At some point, we stop, and then we use this final output to create our semantic map. So just to illustrate this a little bit, what is happening, here's a small region of a parametric SAR image, right, to see all the speckle. Here's the reference data of this region. White means it's not labeled, blue means it's forest, yellow means it's grassland or field, and red means it's building or city area. Now for the first random forest, this is the estimate. It's mostly correct, right? It's already at 86.8% accuracy. That's not that bad, but you also see there's a lot of misclassifications, right? So we have those problems here at the boundaries. Inside of this field, there's a lot of confusion whether this is field or grassland, and so on. And then what we see down here is the uncertainty. Red means the random forest is very certain in its decision, and blue means it's very uncertain in the decision. So it's it doesn't really know what's doing there. So this is the first level random forest. So it's this guy over here. So now let's see what happened when we are using this one. So this is first level. So this is the second level. And I just toggled back a little bit between those two. And first of all, you see the accuracy jumped from 86 to 88. So we gained 2% of accuracy by doing that. Many of the mistakes, in particular inside here of this field, right, they are going away, and lots of the uncertainty is also going away, right? It's getting much more certain. Now we go to the third level. Again, we gain 1% in accuracy, right? We jump from 88 to 89%, right? The noise gets a little bit better. Uncertainty is also getting lower, and then we just continue. 5th level, 6th level, 7th, 8th. And now you can see that it's not changing much anymore. Now it's just starting to fluctuate a little bit, right? It's just flickering, but it's not improving much anymore. And at level 10, I just said, okay, it has converged, didn't change for like 4 levels now, so I can just stop it. So now it's still not perfect, of course, right? So there are still mistakes, right? We only have an accuracy of around 91%. But it's much better. We started with, what was it, 86 or something. And the uncertainty also got much better. So we can actually quantify that. So what you see here is the number of stacking levels from 0 to 20. The blue one here is the kappa statistic. So this is an accuracy measurement, and you can see it's increasing, and then it just converged. It's not changing anymore. The red curve is also a type of an accuracy measure, and the blue one is an uncertainty measure. So also for the uncertainty, it's improving. So this means that on the one hand, by doing this kind of stacking of the random forest, accuracy is improving, the uncertainty is getting better, and it's not overfitting, right? It's not like it's going down again, right? So this is results on test data, of course, right? So overfitting would mean at some point it's going down again, because it's just memorizing the data. That's not happening. At some point, it's not worth continuing, right? At level, more or less at level 5 already, we are converged. You can go a little bit more just to be certain, but latest at level 10, you see nothing is changing anymore. So then you can just stop, and then you're done, and you can compute whatever kind of final product you want based on the class posterior that you got. This here shows the calibration of the model. So calibration means how trustworthy those probabilistic estimates are. This is from the first level, and you can see if you average over all the classes, it actually looks quite okay. So the optimum calibration would be this diagonal. For some classes it's overconfident, and for other classes it's underconfident. But now if you move forward to the last level, right, it's still not perfect, but it got much better, right? So again, the optimum would be the diagonal, right? And the curves that were down here, they were, pulled closer in that direction. And the curves that were up here, they got pulled in that direction. So they're both closer now to the diagonal. So we also can visualize this a little bit better. So in this graph here on the right, what I did was, for the different stacking levels, I just computed the difference between the corresponding calibration curves to the diagonal, right? So the optimum value would be at 0, right? That means it would be perfectly calibrated. We hit exactly the diagonal. And you can see that everything is going towards the diagonal, right? So the blue one, that was the road, also this one here, those are here, they were underconfident, so they were also improving. The red one is a little bit weird, right? It started above the diagonal and ended up below it, but I mean, still, it's not getting worse, and it's converging at least. All right, but what about deep learning? So now you know what is random forest, you know what is stacking random forest, but you might ask yourself, but should I really do that? Do I really need to know that, or isn't today everything I need to know is deep learning? So let me show you one example why it's important to know this. So let's assume you want to do semantic mapping, right? So we have a radar image. In this case, it's Sentinel-1. We have a few hand-labeled samples, and we want to create a semantic map like this, right? So we have a training data set that is razor small. We want to train our classifier on that and then apply it to a different region in order to get a full semantic map like this. And if you do that with different amount of data, so here on the left hand is when you use all the amount of data that we had for this particular case. And down here, it's like if you only have a 16th of all the data that we have. And then the violet and the blue one is two different deep learning approaches, different versions of a UNet trained from scratch on this data. And the green one is the random forest we just discussed, that is learning automatically the features from the data. And you see the random forest is outperforming the deep learning approaches by quite a bit, actually, if you have only a little bit of data. The distance is getting smaller the more data you have, and at some point, if you're lucky and you choose the right deep learning architecture, you're outperforming the random forest. If you're not so lucky and you use the wrong deep learning architecture, the random forest actually still performs quite competitive. So this means if you don't have a lot of data and you don't have a good idea of doing self-supervised learning or pre-training, then a random forest like this might give you an advantage. It's super easy to set up, easy to implement, very efficient. You can visualize it, you learn something about your data, and at the end, you're getting a better result than with deep learning. And even if you increase the number of samples, random forest stays competitive for quite a while. If you increase the number of samples more and more and more, at some point, the random forest will be harder to train, because you need to restrict the tree growth, because otherwise it's not fitting into memory anymore. While the deep neural network can just, doesn't matter how much data you fit in. The more data you have, the bigger models you can use, and performance will get better and so on. So at some point, if you really have a lot of data, then random forest won't perform as good anymore. If you don't have so much of data, random forest might actually be the better choice. One thing you can't do with random forest, though, is pre-training or self-supervised learning. So optimizing, the network on a different task than the final network. That's something you can't do with a random forest. And one thing we tried was pre-training a network by transcoding. So we wanted to take a radar image and produce an optical image. And then the features that have been learned by this task, not the optical image, this one we throw away, but the features the neural network learned for this transcoding task, we then used as an input to a classifier, just as input to another neural network. And since those features are already very, very strong, this segmentation network can be quite small, and then you only need a small amount of labels in order to train it. So this is something you can only do with neural networks. You can't do that with a support vector machine. You can't do it with a random forest. Neural networks, you can do that. And that actually works quite well, right? So this is the same graph as before. The random forest is down here. The two deep neural networks that were trained from scratch are down here, right? Random forest is better. But if you do this type of pre-training, then the neural network is outperforming this by quite a bit. And it's stable no matter how much data you use, right? So even with a small amount of data, you already get quite good results. So bottom line is deep learning works. So don't take as a take-home message, don't understand. I talked for like 70 minutes now about random forest because deep learning doesn't work. Deep learning does work, and it won't go away. It has a lot of advantages. But in many areas, for many problems, a modern shallow learner, as long as it's not like a support vector machine or something like that, will probably also work. And if you're not have a lot of data and you don't have a good idea or the computational resources in order to do a good pre-training, either self-supervised or in any other way, then probably a modern shallow learner will outperform a deep neural network that is trained from scratch. All right, so the take-home message I want you to remember is, as scientists and as engineers, we should have a toolbox, and we should be able to pick the right tool for the job at hand and apply it in the right way. Sometimes this will be a deep neural network, and sometimes this might be something else, for example, a random forest. And hopefully now you have a better idea what a random forest is and what you can do with that. Okay, and with this, I'm at the end, and I'm here for questions if there are any.
Yeah. Thank you so much, Ronnie. Ashwini ma'am?
Yeah. Thank you, Dr. Ronnie sir, for sharing your valuable insight with us. Yeah, now we'll engage a Q&A session. Participant, please feel free to ask questions.
Hello, Dr. Ronnie, is Prakash here? Can you hear me?
Yep.
Hello, can you hear me?
Yes, I can hear you.
Yeah, thanks. So you were showing one slide earlier about limited samples, and then you are trying to adapt something from, the images earlier. So does this refer to some kind of a domain adaptation approach that you are using to improve this accuracy here?
No, it's not really domain adaptation because you always apply to the same data set. So there's no shift in your data distribution. It's more a refinement in what you have trained. So what the stacked random forest is really doing is just learning to correct the mistakes the previous random forest has done on the same data, right? So you only apply to the same training data set that you have used. And this pre-training set here, I mean, the pre-training is done on a different region as the final labeling, but
Yeah.
the statistics should still be quite similar to each other, right? So you can't train it over a forest area and then you apply it over, like a desert area. That won't work very well because the features you have extracted are descriptive for this specific area. So it's not so much domain adaptation; it's more like a certain way of fine tuning the features you have computed or the predictions that you made.
Okay. So then can we augment data from multispectral or hyperspectral images to the features of the star
Yeah,
images? Yeah.
yeah, yeah. It's no problem at all. I mean, the problem is the data processing, right? You need to align the data that one pixel corresponds to the same object on the ground in both imagery, right? So this is a little bit in a challenge, but it's an engineering challenge, right? So you need to make sure if you want to do data fusion, no matter how, if you want to do data fusion, your data needs to be aligned. But for the random forest, it's completely fine. You can have data from different modalities, and you don't need to worry about normalization of the data or whatsoever, because the random forest in every node test it's testing, it will only pick one of the modalities, right? It won't combine it with the other modalities. Then overall, all the nodes together will combine the different modalities, but a single node test won't. So I have another work. I didn't do it with radar data there, but there I had hyperspectral data, um,
Mhm.
high resolution RGB data, and multispectral LiDAR, so depth laser data. So those three also quite different modalities, and it's no problem to combine them in a random forest.
Yeah. Thank you. Thank you, Dr. Dan.
That's actually the beauty of this type of random forest, because the only thing you need to change is, if you remember this plot here, the only thing you need to change is this distance metric, right? So the operator gives you a pixel value, and then this distance metric needs to be data dependent. If it's a radar image, you choose a radar distance metric. If it's a hyperspectral one, you choose a distance metric that is, that is working over hyperspectral signatures.
Yes, yes.
So the overall framework stays the same. You don't need to change anything, just this distance metric. And the other nice thing is, if there are multiple distance metrics and you don't know which of them to use, you can just include all of them and let the random forest figure out which one works best. Right? So this is really the nice thing. Um, if you don't know which one to use, just put it in. Random forest will figure it out for you, which one to use.
Okay. Okay. Yeah. Thank you. Thank you so much.
Yeah, one more question, sir. Yeah, on behalf of participants, I'll ask you one question. Can we integrate features from both hyperspectral or multispectral images along with SAR images to improve classification using random forest?
Yeah, I think that was the question that we just discussed. Yes, you can. It's no problem. You can include the raw data, so you can include the directly the spectral signatures, and the random forest will compute spatial spectral features based on that. But if you have a certain idea that a certain feature is working very well for your specific application, so maybe you want to do, a forest non-forest map, then you can include like a vegetation index, for example, that you can compute from multispectral data. So if you know there is a certain feature that works well in your application, you can also include it additional to the raw data. And the random forest can just work with it. It's no problem.
Okay. Yeah, thank you, sir. It's now time to express our heartfelt gratitude to our esteemed expert. Hello. Hello.
Hello.
Yeah, you want to ask question?
Yes, ma'am. Actually, I'm just go through one your reference research paper, that is the colorful tree and visualization and interpretation of the random forest. Sir, can you provide any additional references of that paper to visualization of random forest, or any Python libraries available?
So in that one, there should be a Git repository, a link to it. If you can't find this, just write me in email, and I can send this to you.
Okay. Okay, sir. Okay. I will mail you.
Mhm.
Definitely.
Yep.
Yes, sir. Yes, sir.
Yeah, participants, do you want to ask any questions? Yeah. Okay, it's done. Yeah. So it's now time to express our heartfelt gratitude to our esteemed expert, Dr. Ronnie, for his insightful presentation on classification of polarimetric SAR images by stack random forest. Sir, we are deeply thankful for the time and expertise you have so generously shared with us. Your session has provided us with valuable perspectives on the various aspects and applications of GeoAI in working with the classification models, interpretation, visualization, and its optimization. Thank you for inspiring us and enriching our understanding of this cutting edge topic. Thank you once again, sir. Thank you so much.
Thank you for having me. And
Yeah,
bye bye, everybody.
yeah, thank you so much.
Thank you, sir.
Yeah, thank you, sir. Bye.
Hello.
Yes, sir. Yes, Digambar, sir, you want to convey something?
No, yes. We'll wind up today's session and we'll meet tomorrow at
Yeah, yeah.
before 6 p.m.
Yes, yes.
Participants link is there in the chat box, so you can use this. Attendance link is there.
Attendance feedback, the link is in one only. Yeah.
They're asking to share it
Share
again.
it again. Yeah, yeah. I will share it.
So we'll keep this meeting on 5 minutes for hold. So participants can use this attendance link. Then after that we'll close this meet. Participants are requested to fill the attendance. Sandeep sir.